but it sounded like...
I'll
right.
talk to him. And you want to do your...
No.
So,
Well, I mean, I'll explain what it is when we're done, but...
give him a minute and then... Oh, if I forget, you tell me. Nathan is in fact back today. He's asking yesterday. All right, good morning. I think we'll get started. Yesterday we started our study of respiratory physiology, and today we're going to take a deep dive into gas exchange. The next two lectures will deal with gas exchange. I will do the first part, and Dr. Bowman will take over for the second half. I still have no relevant financial or commercial interests. Haven't made any new relationships in the last 24 hours. There is going to be more math in this lecture, but it's all pretty straightforward. Our learning objectives for today are to understand how oxygen moves from the alveoli to the blood and what properties of the blood-gas barrier affect the transfer. We're going to talk about the oxygen-hemoglobin dissociation curve. You should understand the difference between different oxygenation metrics, and a big focus of today at the end is going to be looking at the alveolar gas equation and using that to determine P big A O2, or alveolar oxygen tension. Again, we have some reference slides here. We're going to be talking a lot more about gas exchange and gas transport today, and your abbreviations. So let's go back to this schematic of the lung with our conducting airway, alveolus, and our pulmonary capillary here. Yesterday we talked about how gas moves in and out of the alveoli, and we call that ventilation. And today we're going to focus on this area down here. We're going to fix on gas exchange, which is the transfer of gases across the alveolo-capillary membrane, otherwise known as the blood-gas barrier. And I'm probably going to call it the blood-gas barrier because that's a lot easier to say than alveolo-capillary membrane. All gas transfer occurs via passive diffusion. There's no active transport of gas across this membrane. And diffusion, as you remember, is just a chemical process in which molecules move from areas of high concentration with lots of molecules to areas of low concentration with fewer molecules. We talked a lot about carbon dioxide yesterday, which is intricately tied to the concept of ventilation. And today we're going to focus more on oxygen. And yesterday we established that the PO2 of inspired air at sea level is about 150 millimeters of mercury. Normal alveolar PO2, we'll say, is around 100 millimeters of mercury, and a normal arterial oxygen tension of blood returning from the tissues to the right side of the heart and then to the lungs, otherwise known as mixed venous blood, is about 40 millimeters of mercury, just to give you some benchmarks. So that you can see there's a gradient from the alveolus, which has a high concentration of oxygen molecules, 100 millimeters of mercury, to the pulmonary capillary blood, which has a lower concentration of oxygen molecules, with the partial pressure of only 40 millimeters of mercury. And Fick, who was a German physician and physiologist in the 1800s, derived this equation describing the process of diffusion. You should already know Fick because you just had cardiology, and it's the same guy who figured out how to calculate cardiac output. And Fick's law describes gas transfer across a membrane, looking at several factors, including A, which is the surface area of the membrane, T, the thickness of the membrane, D, a diffusion constant, and this difference in partial pressure of the gas across the membrane. And the diffusion constant is proportional to the solubility of the gas that's diffusing across and inversely proportional to the square root of the molecular weight of the gas. So let's look at how Fick's law of diffusion applies to our gases of interest, oxygen and carbon dioxide, across our membrane of interest, which is the blood-gas barrier. So first we see that diffusion across the membrane is proportional to the surface area of the membrane. The surface area of the membrane, as Dr. Bullman told you on Monday, is very, very large. It's estimated to be anywhere from 30 to 100 square meters, depending on how old you are and how tall you are. And just to give you a sense of size, this house has 90 square meters of habitable living space, so it's a very, very large area in your lungs. That we know from this law of diffusion that the diffusion across the membrane is inversely proportional to the thickness of the membrane. And it turns out that the blood-gas barrier is very, very thin. It's only about a third of a micron in many places. We also know that diffusion is proportional to the diffusion constant. So far in the normal human lung, we know that we have a very large A and a very small T, and then we have this diffusion constant. The gases that we're talking about primarily, carbon dioxide and oxygen, have fairly similar molecular weights. Carbon dioxide is a little bit bigger than oxygen, but not standards of deviation apart. Whereas carbon dioxide is much, much more soluble than oxygen. And therefore, carbon dioxide diffuses through the blood-gas barrier about 20 times more rapidly than does oxygen, which is important, and that's one of the main reasons why our P big A CO2 and our P little a CO2 are essentially interchangeable values. Just to sum up, the factors that affect transfer of gases across the blood-gas barrier include surface area of the membrane, thickness of the membrane, solubility and size of the gas, and the pressure gradient across that membrane. Let's now take a look at some specific diffusion properties of different gases moving into the capillary from the alveolus. We're going to hone in on that alveolar capillary membrane interface, and for the next several slides we're going to ignore gases leaving the capillary for the alveolus and focus specifically on gas diffusing into the capillary from the alveolus. The red tube here is a capillary, so we're going to add a red blood cell and some dissolved gas, and the blood in this capillary flows from left to right. At the beginning of the capillary is the blood before gas exchange has occurred, and at the end of the capillary is the blood after gas exchange has occurred. We can also think of this pre-gas exchange blood as mixed venous blood returning from the tissues, and this post-gas exchange blood is arterial blood. So when our red blood cell enters that pulmonary capillary in the region of gas transfer, how rapidly does it take the partial pressure of your gas of interest in the blood to rise? The time it takes for a single red blood cell to travel through the whole gas transfer region of the pulmonary capillary is typically about 3/4 of a second in a normal human at rest. How fast, so our question is really, how fast does a gas diffusing across this membrane reach its equilibrium point in terms of partial pressure? Does it even do so? And as is often the case with human physiology, the answer is it depends. So this graph is something that we're going to focus on for the next couple of slides. The x-axis here is just time in the capillary with a starting point of 0 seconds and a finishing point of 0.75 seconds. And the y-axis is just partial pressure of our gas of interest. So during this whole time, gas is being transferred across the blood-gas barrier via diffusion. And we're looking at how quickly the gas rises from its starting pressure to its ending point. The ending point might be alveolar pressure. Partial pressure of the gas in the capillary cannot exceed alveolar pressure because diffusion doesn't work that way. We go from high concentration to low concentration. So the highest the partial pressure in the capillary can reach is alveolar pressure. Otherwise, it would start flowing the other way. So we're going to look at carbon monoxide first. Carbon monoxide binds very, very avidly with the hemoglobin in red blood cells. And in a real human, this property is very dangerous and potentially lethal, and you're going to learn about this in the next lecture. For right now, we don't have to worry about carbon monoxide poisoning because these aren't even real lungs. We're just talking about gas transfer across the membrane of our fake lungs. So carbon monoxide moves very rapidly across the blood-gas barrier into the red blood cell, and the content of the carbon monoxide inside the red blood cell rises because hemoglobin is basically acting as a sponge and binding up all this carbon monoxide that's coming across that blood-gas barrier. So there's not a whole lot of carbon monoxide left over to increase, to dissolve in the blood and increase partial pressure in the blood. Because there's no buildup of back pressure, that carbon monoxide can just keep flowing across that membrane down that diffusion gradient, or down that pressure gradient. So the amount of carbon monoxide that actually gets into the blood is limited only by the diffusion properties of the blood-gas barrier and not at all by the amount of blood available. And we refer to this type of gas transfer as diffusion limited. And this is what it looks like on the graph. Now we're going to look at the opposite end of the spectrum at a different gas called nitrous oxide. And you probably all know nitrous oxide is laughing gas. It's something that's been used in medicine for over 150 years, typically in dentistry where it's used as an anesthetic and analgesic agent. It turns out to be a very weak general anesthesia agent, which is why we don't use it in surgery anymore because it's a bad thing if your patient wakes up in the middle of an appendectomy. So the key point to this discussion is that nitrous oxide does not bind with the hemoglobin in red blood cells, which is the opposite of carbon monoxide. So when nitrous oxide moves across that blood-gas barrier, no combination with the hemoglobin occurs. It's all being dissolved in the blood. And consequently, the partial pressure of nitrous oxide in that capillary blood rises very, very rapidly. And only a tenth of the way along the capillary, your partial pressure of nitrous oxide in the blood is pretty much the same as your alveolar partial pressure of nitrous oxide, and no more nitrous oxide is transferred. So the amount of nitrous oxide that gets taken up by the blood depends entirely on the amount of available blood flow. So we call this kind of gas transfer perfusion limited, and it looks like this on our graph. But we don't really breathe carbon monoxide or nitrous oxide. We're interested in oxygen. So what happens with oxygen? Oxygen falls somewhere in the middle. It combines with hemoglobin, so it's not, unlike nitrous oxide, but it doesn't combine with hemoglobin as avidly as carbon monoxide. So there is rise in capillary pressure of the oxygen. It's just not as fast as carbon monoxide. That said, under typical resting conditions, normal lungs, capillary PO2 just about reaches alveolar PO2 just a third of the way across that capillary. So under normal conditions, we say oxygen has a perfusion-limited property. However, if you have diseased lungs with impaired diffusion due to, say, deposition of fibrin and other materials along that blood-gas barrier, so the membrane is thickened, it might take a long time for your arterial PO2 to rise to alveolar PO2, and you might fall down to this line here, the pink one. And if your diffusion is very severely impaired, it might take you the whole transit time through the capillary for your alveolar PO2, or for your capillary PO2 to get up to alveolar PO2, and you might not even quite make it. In that instance, oxygen transfer becomes diffusion limited as well. So two points. The first, with carbon monoxide and nitrous oxide, our starting point was 0. But the blood returning to the heart already has oxygen in it. Your mixed venous blood already has a partial pressure of 40. So that's why your curves start there. The second point is that even though we've drawn this graph is drawn such that the oxygen partial pressure of the capillary really reaches the alveolar pressure, that's not actually true in a real person. The end capillary PO2 never quite reaches alveolar PO2. And that's because of something called shunt from the bronchial circulation. So this is unoxygenated blood being dumped into this system that lowers end capillary PO2. And you're going to learn about shunt in the next hour as well. So just file that away. So we've established the properties of oxygen transfer in the normal human lung at rest when capillary transit time is about 3/4 of a second. What happens if we speed up that transit time? If you exercise, your cardiac output increases anywhere from 6 to 7-fold, and as a consequence, pulmonary blood flow is markedly increased. And capillary transit time can speed up so much that you might decrease that time to only 1/4 of a second. Which means that the time available for oxygen to get across that blood-gas barrier is significantly reduced. So this dashed line here represents the new point at which blood exits the gas exchange space. So here's your starting point and here's your ending point. And we see that in the normal lung, you've already gotten up to your alveolar pressure, or just about, in that time. So in the normal lung, this doesn't matter. Arterial PO2 is basically at its maximal levels, even with that shortened time in the gas exchange region. And we say that the normal lung has enormous diffusion reserves. The diseased lung can be a very different case. If we're starting out on this lower trajectory here, and at rest it takes you almost the whole time in the capillary to get your capillary PO2 up to near alveolar PO2. Shortening that time can dramatically reduce your PO2. And that's one of the explanations why people with thickened alveolar capillary membrane, such as in pulmonary fibrosis, desaturate pretty severely with exercise. So we've discussed ventilation, how air moves from the atmosphere to the alveoli. We've looked at how gases move across the blood-gas barrier, which we call gas exchange. And now we're going to look into the blood and see what happens to oxygen when it's in the blood, which we call gas transport. Oxygen in the blood, as you probably already know, is carried in two forms. There's dissolved oxygen, which is what we've been primarily talking about so far. And then there's oxygen combined with hemoglobin. And we're just going to look at oxygen dissolved in the blood as this dioxygen molecule, and oxygen bound to hemoglobin with these red blood cells. So the amount of oxygen that gets dissolved in the blood is proportional to the partial pressure of oxygen, which is P little AO2. And we know that for humans, there are 0.003 of a milliliter of oxygen dissolved per deciliter of blood for every 100 milliliters of blood. And that's what it looks like more. This is more representational, pre-gas exchange, post-gas exchange. So if you have normal arterial blood that has an arterial oxygen tension of about 100 millimeters of mercury, you get about 1/3 of a milliliter of oxygen per deciliter of blood being transported as dissolved oxygen. So is that a lot? This is Mary Cain. Mary Cain is a really, really fast runner. She's the 2014 World Junior Champion in the 3,000-meter run. She's considered to be the best female American middle distance runner since Mary Decker Slaney, who you're probably all too young to know. And she's also the daughter of an anesthesiologist here at Columbia. Mary wins a lot of stuff. So how much oxygen is being delivered? That's her, I think, actually at the, just after she won the junior world championships. So how much oxygen is being delivered to Mary's muscles as dissolved O2? So her cardiac output at rest, we'll say, is 5 liters per minute. It's probably more because she's a highly trained athlete, but just for our purposes, it's 5 liters per minute. When she runs, her cardiac output increases 7-fold up to 35 liters per minute. So if she has a PaO2 of 100 millimeters of mercury, her dissolved oxygen is 1/3 of a milliliter of O2 per deciliter, as we just said. And if we'll just convert it into liters, 3 milliliters per liter. So the total amount of oxygen she can deliver to her tissues is her cardiac output times her dissolved oxygen concentration, 105 milliliters of oxygen per minute. That sounds like a lot, except that her tissue requirements are on the order of 3,000 milliliters of oxygen per minute. So clearly there's an additional method needed for transporting oxygen to her tissues. And that's where hemoglobin comes in. So we're going to talk only about normal adult hemoglobin, which is hemoglobin A, and defer discussion of pathologic hemoglobin forms like S and C to your hematology section. So heme is an iron porphyrin compound. Globin is a tetramer with 4 polypeptide chains, 2 alpha, 2 beta. And together they form hemoglobin. And oxygen has an easily reversible combination with hemoglobin to form oxyhemoglobin. And the important thing is that each hemoglobin molecule can bind up to 4 molecules of oxygen. And just as a reminder, we describe a molecular interaction as cooperative when the interaction of one molecule influences the subsequent interaction with another molecule. And hemoglobin binds oxygen in such a cooperative fashion. The more molecules of oxygen that are bound to hemoglobin, the easier it is to bind the next one to load up all the sites until all 4 sites are fully occupied. And the reverse is also true. Once you start unloading oxygen molecules, it becomes progressively easier to do so. Oxygen capacity just refers to the maximum amount of oxygen that can be combined with hemoglobin when all the binding sites of all the red blood cells in the arterial blood are occupied. And you can find that out experimentally by putting a non-rebreather face mask on someone and having them breathe 100% FiO2, so all of the gas that you're breathing is oxygen, and measure the blood invasively and subtract the dissolved oxygen. We're not going to worry about that right now. Just know that 1 gram of pure hemoglobin can combine with 1.34 milliliters of oxygen, and for a normal person with normal hemoglobin concentration of 15 grams per deciliter, normal oxygen capacity of this hemoglobin is about 20 milliliters of oxygen per deciliter of blood. Oxygen saturation of hemoglobin is a very, very useful clinical tool. And this is just how the percentage of all the hemoglobin binding sites that actually have oxygen attached. So mostly on the wards, you're going to talk about oxygen saturation of arterial blood, the SaO2. But you could also use this concept to talk about the saturation of mixed venous blood as well. This is the oxygen hemoglobin dissociation curve, and we're going to spend a few moments talking about this. PaO2, or the partial pressure of the dissolved oxygen, is on the x-axis. SaO2, or the percent saturation of hemoglobin with oxygen, is on the left-hand y-axis, and then total oxygen concentration, oxygen content, or just the total amount of dissolved oxygen plus oxygen bound to hemoglobin, is on the right-hand y-axis. This is the original graph from John West, who's the preeminent lung physiologist. And this graph actually takes us all the way out to that situation that I was referring to, where people are breathing 100% FiO2 to determine total oxygen capacity. And we don't really need to see that part of the graph for our purposes today. So let's just look at the section of the graph where people are breathing FiO2 21% in normal atmospheric air. So this curve has several important characteristics that I'm going to point out. First, notice the sigmoidal shape. This shape is because there's cooperative binding. If there weren't any cooperative binding, the relationship would be nonlinear. Would be linear between PaO2 and SaO2. The second thing is, look at how much contribution to total oxygen content is made by dissolved oxygen versus oxygen combined with hemoglobin. This, very small. This, the bulk of what oxygen is being carried in the blood. Second, here in the lungs, immediately post-gas exchange, PaO2 is about 100 millimeters of mercury. Oxygen saturation, 100%. Over here in the tissues, or the mixed venous blood, PaO2 is about 40, and hemoglobin is 75% saturated with hemoglobin. And the difference between this total oxygen content over here is the amount of oxygen that was unloaded to the tissues to supply fuel for cellular respiration. The other interesting thing about this curve is up here on the flat end, you can move PaO2 a lot. You can drop PaO2 all the way from 100 down to 60, and you drop oxygen saturation only a little bit. So here you have a 40-point drop in PaO2 with only a 10% drop in oxygen saturation. If you move down the curve to the steeper part, even small changes in PaO2 equal bigger changes in SaO2. So dropping PaO2 from 80 down to 50, which is a 30-point drop here, drops your oxygen saturation from 85 down to about 45%. So the changes are much more profound when you're in the tissues or near the tissues and on that steeper part of the curve. It becomes much easier to unload oxygen in that situation. Several factors can alter the shape of that oxygen hemoglobin dissociation curve. For instance, increasing hydrogen ion concentration or lowering pH moves the curve right, whereas a lower hydrogen ion concentration or more alkalemic blood moves the curve left. And what does it mean to shift the curve? If you shift the curve right, it means it's easier to unload oxygen from hemoglobin at any given PaO2, and leftward shift is the opposite. Hemoglobin will more avidly bind oxygen at that given PaO2. So here, at a normal pH of 7.4, we know that at a PaO2 of 40, SaO2 is about 75%. If you drop your pH to 7.2, which is a higher hydrogen ion concentration, here at our PaO2 of 40, hemoglobin is only 60% saturated with oxygen. Temperature also shifts the curve. Fever shifts the curve right. Higher temperatures, lower temperatures will shift the curve left. The partial pressure of your carbon dioxide will also shift the curve. Increased PCO2 will shift the curve right. Lower PCO2 will shift the curve left. This all happens, or it's primarily mediated by the actions of PCO2 on hydrogen ion concentration. And that's actually called the Bohr effect after Niels Bohr. 2,3-diphosphoglycerate is an end product of red blood cell metabolism. It binds to the beta chain of reduced hemoglobin, and it lowers hemoglobin's affinity for oxygen, facilitating oxygen's release to the tissues. So more 2,3-DPG shifts the curve right, and less 2,3-DPG shifts the curve left. And there are several conditions that can raise or lower your 2,3-diphosphoglycerate concentration. So you see that increasing your PCO2, temperature, 2,3-DPG concentration, and hydrogen ion concentration all shift the curve right. And you can kind of remember that because if you have exercising muscle, it's acidic, hypercapnic, and hot, and it does better if you are able to give it more oxygen. All right, so we've established pretty firmly at this point that oxygen is carried in the blood in two forms. Total blood oxygen, or arterial oxygen content, which is abbreviated CaO2, is just the sum of those, the content contributed by each of those forms. So we've already calculated dissolved oxygen content. We know it's 0.3 milliliters of O2 per 100 milliliters of blood in our normal person with all those variables that we've already established. We know that 1 gram of hemoglobin carries 1.34 milliliters of oxygen. The content of the oxygen that's bound to hemoglobin is just 1.34 times the amount of hemoglobin that you have times how saturated it is with oxygen. So if we're taking all of these pretty standard values, we find that the content, the arterial oxygen content bound to hemoglobin is about 20.1. We can do this with venous blood too, because there's about 5 milliliters of oxygen per 100 milliliter of blood dumped in the tissues. During normal resting circumstances, the content of oxygen in venous blood is about 15 milliliters of oxygen per deciliter. And total content of the blood, total oxygen content of the blood is just the content of oxygen bound to hemoglobin plus the content dissolved in the blood directly. And we can see that together that's about 20.4 milliliters of oxygen per deciliter under these pretty standard conditions or ideal conditions. And getting back to this west curve, this is just the left-hand y-axis. So let's look at what happens to our oxygen hemoglobin dissociation curve if we change the concentration of hemoglobin. So the y-axes on this graph are flipped horizontally from the prior ones. So total oxygen content is now on the left-hand side of the graph, and oxygen saturation of hemoglobin is on the right side with a different scale for each level of hemoglobin that we have. So if we start out with a hemoglobin of 10 grams per deciliter, which is anemia, we see that the hemoglobin is still 100% saturated at a PaO2 of 100 millimeters of mercury. And it's still 75% saturated at a PaO2 of 40 millimeters of mercury. And the same is true if we have a hemoglobin of 20 up here, which we call polycythemia. Here at our PaO2 of 100, it's still 100% saturated. And here at our PaO2 of 40, it's still 75% saturated. The difference is in total oxygen content. Total oxygen content here is very, very different. Lower hemoglobin levels have less vehicle to carry oxygen around in the blood. So the total content is much, much lower at a hemoglobin of 10 versus a hemoglobin of 20. We've talked about several different ways to measure oxygen in the blood. The P-little-a-O2 and the S-little-a-O2 all come from an arterial blood gas. An ABG is painful. It's more painful than a venous blood draw. It's a little bit more technically difficult and requires a higher level of training. A phlebotomist doesn't draw an ABG. It either has to be a doctor, a nurse, or a respiratory therapist. And an ABG gives you information at one point in time rather than continuous data. So we've evolved non-invasive measures such as a pulse oximeter to give us more continuous data with less pain. And a pulse oximeter just has a probe that shoots out two wavelengths in the infrared and red range. And oxygenated hemoglobin and reduced hemoglobin absorb these differently, so you can calculate the oxygen saturation of hemoglobin. And there's very, very high correlation between the SpO2 and the SaO2. So we've talked a lot about ventilation, gas exchange, carriage of oxygen through the blood and its two forms. And this slide reminds me to tell you that no matter how vigorous your ventilation, and how much hemoglobin you have available to bind oxygen, no oxygen gets delivered to the tissues without blood flow. Oxygen delivery to the tissues depends on both arterial oxygen content and cardiac output. And if we look back at Mary here, we see that she has a cardiac output of 35 liters per minute. We've established that her total arterial oxygen content is 20.4 milliliters of O2 per deciliter, or 204 milliliters of O2 per liter of blood. So her oxygen delivery is potentially 7 liters of oxygen per minute, which is more than enough for what her tissue needs are. All right, we've been in the blood for a while, so let's move back to the alveolus so that we can talk about the alveolar gas equation. This is one of the most important physiologic relationships you'll learn in your whole body in health and disease class, and it's certainly one of the most important things we'll talk about in respiratory physiology. And we're going to start by talking again about the flow of gas across this blood-gas barrier. And first, we're going to return to carbon dioxide for a few moments. This term, V dot CO2, refers to the rate of transfer from the capillary into the alveolus. Another way to think about V dot CO2 is at the tissue level, how much CO2 is being generated by cellular respiration. And just schematically. So if the tissues are putting 200 milliliters per minute of carbon dioxide into the blood, which is a typical metabolic minute production, the lungs are going to have to eliminate 200 milliliters per minute of carbon dioxide from the alveoli to keep your arterial carbon dioxide concentration at a steady state. V dot CO2 is something that's typically preserved even well into significant lung disease because of the solubility of carbon dioxide, which we've already talked about. Oxygen is different. V dot O2 can be thought of as going in the opposite direction, and when we use this term, we mean transfer from the alveolus into the capillary or uptake by the tissues from the capillaries, the opposite direction. So the tissues are extracting 250 milliliters of oxygen per minute, and that's a normal consumption at rest, both as dissolved oxygen and oxygen bound to hemoglobin from the blood. And the lungs need to be able to supply all of that fuel, that 250 milliliters of oxygen per minute from the air, from alveolar gas specifically, to fuel tissue needs and keep arterial oxygen concentration the same in a steady state. VO2, unlike VCO2, is very much affected by lung disease. And you're going to talk specifically about ventilation and perfusion matching and mismatching very shortly. So how do we relate these two opposite processes of oxygen being consumed or taken up and carbon dioxide being produced and eliminated? We can use something called the respiratory quotient. This is just a ratio of carbon dioxide production to oxygen consumption at the tissue level. Lots of different factors affect respiratory quotient. Some make intuitive sense when you think about metabolism, things like fever, activity, and even metabolically important hormones. The food that one consumes, and in turn the fuel that you provide for cellular respiration, also has a major impact on respiratory quotient. With an all-carbohydrate or all-glucose diet, 1 molecule of carbon dioxide is produced for every molecule of oxygen that's consumed, so RQ equals 1. We're much more metabolically efficient with an all-free fatty acid diet, for instance. So for every 10 molecules of oxygen that are consumed, only 7 molecules of carbon dioxide are produced. So RQ in that instance is 0.7. With a typical Western diet, RQ is generally around 0.8, and that's the number that you'll mostly need to remember. It's really, really hard to measure RQ because it's right down at the level of your cells, and it's just very complicated. And it's one thing if you're sacrificing animals in a laboratory. That's generally frowned upon when you're taking care of patients. So fortunately, we have a correlate at the mouth, which is the respiratory exchange ratio. Measuring the respiratory exchange ratio isn't easy. It involves capturing exhaled gases and measuring them, but it's a lot more practical than trying to monitor cellular consumption. So what this is just the oxygen elimination at the airways, the oxygen consumption at the mouth. So about, and using the values that we've already looked at, 200 milliliters of carbon dioxide are eliminated, 250 milliliters of oxygen are consumed per minute, so the respiratory exchange ratio is also about 0.8. And people are often a little sloppy when they abbreviate these things, so mostly you'll see just R. And no, for your purposes, it's pretty much always the respiratory exchange ratio. And so unless somebody is specifically talking about metabolism at the tissue level, if they're talking about something that they've actually measured, it's very, very likely to be the respiratory exchange ratio. So yesterday, we spent a lot of time and we derived this alveolar ventilation equation. And we learned that alveolar ventilation is inversely proportional to PaCO2. The denominator of that equation should really be the partial pressure of the alveolar gas, alveolar carbon dioxide, minus the partial pressure of carbon dioxide in the inspired gas, so the gas that was already there and not brought in by degas transfer across the blood-gas barrier. But we've kind of already established that there's really no carbon dioxide in inspired gas, so we just dropped it from the earlier alveolar ventilation equation to make things look cleaner. And we're going to put it back here for a moment so that we can compare the equations for carbon dioxide and for oxygen, because this alveolar ventilation equation works for both. And now that we've created these parallel equations, we can get rid of that PiCO2 because it really is essentially zero. And because both of these equations equal the same thing, alveolar ventilation, we can set those two terms equal to each other thanks to the transitive property. And then we can factor out that constant because it's present on both sides of the equation. And that leaves us with the following. And we're interested in alveolar oxygen tension, so let's solve for P big AO2. And when we do that, we see this term. We've just spent a lot of time talking about this. This is the RER. And as I've already said, we don't really measure those two numbers a whole lot because it's kind of clunky. And by clunky, that's what I mean. So that's not a terribly useful thing to do to a lot of patients, although we do sometimes. So we can just sub in our respiratory exchange ratio for the for that V dot CO2 over V dot O2. And this gives us the alveolar gas equation. We know from yesterday's lecture how to find the partial pressure of oxygen in inspired air. We take atmospheric pressure, subtract water vapor pressure, and multiply it by the fractional concentration of oxygen in the inspired air. So we're down to this term. And finally, we've established very firmly by this point that this value here, alveolar carbon dioxide tension, is the same as arterial partial pressure of carbon dioxide. So this is our alveolar gas equation. And it lets us know how much oxygen is in the lungs at the alveolar level. It should be considered a mean value because there's uneven distribution of gas in the lung. That gets back to that ventilation perfusion matching concept that you're going to be hearing about in 15 minutes. And this is used comparing the P big AO2 with the P little AO2 to determine whether gas exchange across your membrane is normal or abnormal. No one is ever in your whole career in medicine going to ask you to derive the alveolar gas equation. If you sampled, 100 pulmonologists, I don't know, how many, 2 of them are going to be able to do that, or 5 of them. Everyone in your medical career is going to expect you to know this equation and be able to use it. This is the single most important blood test in respiratory physiology and pulmonology, so memorize it. So you're all forewarned. This is going to be on your test, and probably in several questions. So let's try it. We can start with some practical examples. So Alice here is a healthy 23-year-old medical student. As part of a research project, she had an arterial blood gas drawn. It was done in the PFT laboratory and sent immediately for ABG analysis. Alice was breathing room air, which we know has an FiO2 of 21%, and the atmospheric pressure in the PFT lab, which they measure, was 765 millimeters of mercury, so slightly different from that 760 that we've been using. So her ABG analysis showed that she had a pH of 7.4, a P little a CO2 of 40, and an arterial oxygen tension, or P little AO2, of 90 millimeters of mercury. So what's her PaO2? This is the way you're often going to see blood gases written. It's just a shorthand convention, and this is just the pH goes first, the PaCO2 goes next, and the PO2 goes last. And then often there we include calculated bicarbonate and oxygen saturation as well. So using our alveolar gas equation, which again you should firmly commit to memory, and our values here of Alice's pH of 7.4, her PaCO2 of 40, and her PaO2 of 90, using atmospheric pressure of 765 millimeters of mercury, we just plug the numbers into the formula, and we find out that Alice has a PaO2 of 100.8 millimeters of mercury, which is a pretty normal PaO2, as we would expect, because she's healthy and has normal lungs. Let's look at our patient from yesterday, Suzanne. Suzanne had the inflammatory colitis and the diarrhea. Suzanne was unfortunately the victim of a adverse event, and she got morphine instead of magnesium. Morphine, as you know, suppresses respiratory rate, and it knocked hers down to 4 breaths per minute. She had her blood gas drawn. The pressure on the wards that day was 758 millimeters of mercury. So her ABG showed a pH of 7.15, a PaCO2 of 75, and a PaO2 of 45. So what is Suzanne's alveolar oxygen tension? So again, this is how we write the gas with pH, PCO2, and PO2. And plugging in these numbers, we find that Suzanne here has a PaO2 of only 55. That sounds pretty low, right? We've been talking about alveolar pressure, about arterial pressure being 40 down at the level of the mixed venous blood when all the oxygen has been taken out. So a starting point of 55 is very, very low. Suzanne doesn't even have lung disease, so why is her PaO2 so low? Why is her? Oh, here. So remember from yesterday, her PCO2 is 75. She has hypoventilation. So hypoventilation is a pretty important cause of hypoxemia. Moving on, and you'll have more of that in the next lecture as well. Our last case, Sean, is a 65-year-old man with pulmonary fibrosis, so he probably has abnormal lungs. In fact, his lungs are so abnormal that he's being evaluated for lung transplantation as part of that workup, which is a very, very comprehensive workup. He had a blood gas drawn in the PFT lab at the same time as Alice. Sean usually uses supplemental oxygen to keep his oxygen saturation up, but today his blood gas was drawn while he's breathing room air, which makes calculations a little bit easier. So his pH was 7.37. His PCO2 is 43, and his PO2 is only 48. So what's his alveolar oxygen tension? Again, that's how you write it. So plugging his numbers in, we find that his alveolar oxygen concentration is 97 millimeters of mercury. Alice has a normal PaO2. Suzanne has a low PaO2, but we know she's hypoventilating. Sean, with all of that lung disease, has a normal PaO2. How's that possible? That's our cliffhanger that we're going to end with, and you're going to find out in 10 to 60 minutes. All right. Questions? Anyone? Okay. Take a break, and we'll reconvene at 10. I couldn't remember where my
dude on the CPED class.
Oh,
I was expecting him like 10 slides earlier, so I was like, holy shit, Dad.
I love it.
Hi.
That was
Yes.
absolutely awesome.
Okay.
That was great.
Do you always use 47 to pH?
Sorry?
The pressure of water in the atmosphere? Yeah. 47 is that constant body temperature. On your body temperature. Yeah, right, okay. And then pressure of water. So if looking at CO2 and VO2 as a ratio, well, if you're looking at the study, do you weight adjust for those?
Not for our purposes.
Yeah.
If you're looking at the actual respiratory exchange ratio, which is probably why you're interested in VO2 here,
And it doesn't matter because that's
your food too is much more important. I mean, there are changes in metabolism.
Say that? Isn't that, tell me, you know the area? I wouldn't say that's guaranteed, but that sounds like that would be reasonable. He'd be a good coach to win with. All right, we're going to get started on the second half of our gas exchange lectures. If you want to take a seat. So just a couple comments before we get started. Lots of different sections will say, oh, this is the most important equation in cardiology or rheumatology or whatever. The alveolar gas equation is something that you will actually use on the wards as an intern over and over and over again. And to answer a question somebody came up, you will have lots of opportunity to practice using the alveolar gas equation in this lecture, in some of the team-based learning modules and so forth. But it really is, there's probably 6 or 8 equations that having in your brain at the front of your mind is actually very important as a clinician, as an intern, as a doctor. So the other thing that I just wanted to point out, this is just a one-board summary of the last elements of what Amy put in, and it's absolutely critically important, and we'll revisit it at the end of my lecture, but get this into your head. Alveolar hypoventilation causes a low alveolar concentration of oxygen. Okay, there's only so much room in that alveolus. If you raise the concentration of one gas, another gas suffers, and that gas is oxygen. And that person in that example had absolutely 100% normal lungs. Gas exchange functioned completely normally in that person. There just was less oxygen because there was more carbon dioxide than normal in that alveolus. And that leads to less oxygen in the blood. Okay, so keep that in the front of your mind, and we're going to move forward. I also developed no disclosures overnight. We're talking very specifically about gas exchange that occurs at the alveolar capillary membrane. The 2 core concepts that you're going to learn about in the beginning of this lecture are what we call VQ matching and VQ mismatch. Understanding V and Q and understanding VQ matching is critical to understanding VQ mismatch. Now, VQ mismatch is the cause of hypoxemia, in many, many, many lung diseases. In fact, it's the most common cause of hypoxemia in lung disease. We already learned one other cause of hypoxemia in lung disease. This is another one, and it's a very, very important one. It also just happens to be one of the more difficult concepts to understand in pulmonary physiology, so we're going to spend the majority of this lecture learning about it. The key to understanding VQ mismatch is understanding how the normal lung matches V and Q, ventilation and perfusion, in a way that optimizes gas exchange, in a way that optimizes getting oxygen into the blood. And it's critical to understand that very slight changes in V and Q and the relationship between ventilation and perfusion causes problems that lead to hypoxemia. Okay. The critical thing to understand at the very beginning is that it's actually the relationship between V and Q, the ratio of ventilation to perfusion, that matters. And there's, this is a slide of the anatomical matching of ventilation and perfusion that I showed you yesterday. Today we're talking about matching of flows, ventilation flow and perfusion flow. Okay, so this is, Amy mentioned, Dr. Atkinson mentioned John B. West, one of the preeminent pulmonary physiologists. A lot of my slides are adapted from his book, and I'll give you the references if you want to look up this book after the lecture. It's quite a thin book, but quite an important one. So picture this contraption, which has some fluid flowing through it. It's a chamber, has a little mixer in it, and fluid is continuously flowing through it. Make that fluid water. And we're going to continuously add little drops of a powder dye to it. So there's flow, and when we're adding this substance, the concentration of what's going on in this chamber, the concentration of this dye is going to be a function of how fast you're adding it and how fast you're washing it away. Okay? Sorry. Say we keep the water flow constant and we start to add dye at 3 times as fast a rate. Concentration in this chamber is going to go up. On the flip side, we keep it at that original addition of dye and we increase the flow of water through this chamber. The concentration of water in this chamber, the concentration of dye in this chamber is going to go down. So the concentration in that chamber is a relationship. It's the ratio of addition to removal. It's the relationship of V to Q. Okay? And that's exactly what we're talking about when we're talking about the concentration of oxygen in the alveolus. Okay? Capillary blood flow is our Q. Addition of atmospheric oxygen by way of ventilation is our V. And the concentration, PaO2, is the result, the ratio of those two things, V and Q. Okay? You can talk about V and Q relationships for any gas, and we'll talk about VQ relationships for carbon dioxide, carbon monoxide, but V and Q determine the concentration in the alveolus of a particular gas. Now, we've drawn this drawing in a variety of different ways to represent the lungs. We've drawn it to represent a normal alveolus or an abnormal alveolus. In this lecture, we're going to talk about lung units, and that's because we're going to talk about regions of the lung. Regions of the lung where a collection of alveoli have similar properties, and different regions in the lung have act differently depending on how much ventilation they're getting and how much perfusion they're getting. So we refer to them as lung units. Just think of them as collections of alveoli that behave similarly. We're going to draw it as a single alveolus. Okay, so this is the ideal normal alveolus that we've sort of built over the last couple lectures based on how much PiO2 is coming down to this alveolus, how much PCO2, which is 0, there's very little in the atmosphere, how much venous oxygen is coming after the body has taken out what it needs. That's what's left over. This is the PCO2 in the blood the venous blood coming to the beginning of this capillary alveolar interface because the body's made carbon dioxide and we're now at a concentration of 45. And this is that ultimate concentration in the alveolus after this equilibrates. So we have a nice gradient for carbon dioxide to move in this direction, a nice gradient for oxygen to move in that direction, and that's our normal lung unit. What Dr. West described in a series of very, very nice experiments on healthy individuals is that the majority of all the lung units in the lungs, in normal healthy lungs, and somebody who's standing upright or sitting upright, have very well-matched ventilation and perfusion. He basically looked at all the various lung units using inert gases and seeing where they moved in a person who was breathing, and he found that if he plotted out all the different VQ relationships in all of the different lung units, that almost all of the blood flow and almost all of the ventilation went to units in a very evenly matched state. They were getting equal amounts of ventilation and perfusion. Okay? You could look at this, and I'll show it on the next slide, as proportion of units. The majority of the units are living in this state, very evenly matched at one. Now, in the little fine print down here, I'll say, if you read in some of the physiology textbooks, some people talk about the normal VQ relationship being closer to 0.8. Forget about that. Just think about it as 1. It's a nice even number. Good, even matching of ventilation and perfusion in the healthy, normal lung. Okay, so you see from this graph that most exist at 1, but there are some units, lung units, down here that are getting less than 1, and some units that are getting higher ventilation-perfusion relationship, a VQ ratio higher than 1. So why is that? That's because your lungs exist in your chest and are affected by gravity, okay? And as a consequence, the force of gravity causes ventilation and perfusion to actually be higher down here. That effect versus relative to up here, that effect is actually a function of the fact, specifically for perfusion, that the heart sits right about there. So this is downstream from the heart, this is upstream from the heart, so we're going to have higher perfusion down there than up here. The same gravity works for ventilation as well, although the relationship is much less dramatic. And you can see it on this slide here. This is basically looking at all the VQ relationships in normal healthy lung as a function of where they are in the chest. So this is the top, the number 1 rib, these are the lower ribs, and you can see that in the lower regions of the lung, blood flow is higher than in the upper region, and same deal, the ventilation is higher than in the upper region, but this is a much steeper drop. And as a consequence, down in the lower portions of the lung, the VQ relationship is actually lower than where it's even, and in the upper portion, it's actually, you have a high VQ in the upper regions of the lung. Okay? So I just drew, these are not random made-up numbers. These are actually the VQ relationships in a normal, healthy person's lung. And obviously, there's a range across this lung. But we're going to think about 3 zones in a normal, healthy, upright lung, where the VQ ratio is actually higher ventilation to perfusion is actually 3 in the upper lung and 0.6. Okay. Just understand that this VQ mismatch, I'll toss that word out now, this arrangement in which some of the units are performing with high VQs and some with low VQs actually goes away to a large extent when you exercise. But let's ignore that, and we're going to talk specifically about the lungs at rest for the remainder of the lecture. So let's think of those 3 regions and plot them out in 3 different lung units. So here we have a lung unit who has a low VQ, and here we have a lung unit with a high VQ, and then the majority of them are living somewhere near normal, and we have the O2 concentration coming down 150 and the CO2 concentration coming down to 0. This is what we get when we look at those ventilation and perfusion relationships. Now, we already just said, and it's up on the board, if we hypoventilate, we're going to have a change in our oxygen. Oxygen's going to go down. This unit is underventilated. This unit is overventilated and underperfused. Okay? And then we have our venous concentration of those gases coming over here. So we have a slightly lower oxygen level in this alveolus, a normal oxygen level in the majority of them, and a slightly higher oxygen level in this ventilated, overventilated. Let's focus for a few moments on this particular lung unit, this low VQ unit. And just to hammer the point home, this lower ventilated unit means that there is less supply of oxygen coming to that alveolus than in this normal unit, okay? And the blood is still removing it, so PaO2 goes down, concentration goes down. Okay? Let's take that to an extreme. Let's forget the normal lung for just 1 second and say, all right, let's take VQ all the way down to 0. This is getting absolutely no ventilation, but blood is still flowing. And let's take VQ all the way to the extreme where VQ is infinity. There's ventilation, but absolutely zero perfusion. Okay? What happens? Well, this alveolus is getting no supply of gas from the outside, and oxygen is basically going to go down to the venous level. And carbon dioxide is going to go down to or up to the venous level, and you're going to have that concentration. Basically, this equilibrates, and you just basically have venous concentrations in this alveolus. Same deal. This alveolus is getting no blood flow, whatever. It eventually equilibrates and just has atmospheric concentrations of oxygen and carbon dioxide. You're going to hear more about these situations later. If you take and graph those lung units from those extremes and plot it out, you get a line like this. Okay? Here's that VQ is 0, where things have equilibrated to the venous state. Here's the VQ of infinity, where things have equilibrated to the atmospheric, and this is where the lungs, for the most part, live. Now, there's clinical scenarios, and we'll hear about them in just a little bit, where this and this are actual states that the lung exists in. People who have been paying attention could recognize that this is actually what happens with dead space ventilation. If there's no gas exchange and you're ventilating something, Dr. Atkinson talked about dead space ventilation yesterday. But the lungs typically exist somewhere on this curve. And basically any alveolus in a normal, healthy person, unless you've changed the venous concentration of gases, is going to have a concentration that falls somewhere on these lines. Okay, so we're going to take and look at those numbers again. This is our low VQ unit. This is our high VQ unit. What's happening to the oxygen being contributed to the blood from these units? Okay, this is just them, again, plotted out into the lung in a person who's sitting upright. So if the PaO2 here is lower, it's going to have to, it obligates, if diffusion occurs exactly the same, we haven't given this person any other abnormality, we've lowered as a result of this change in ventilation perfusion ratio, we've lowered the amount of oxygen coming into the blood. We've lowered the PaO2, the dissolved oxygen, at the capillary after it's gone through this alveolar capillary interface. We have a normal PaO2, and we have a higher PaO2 here. Okay, so we just heard about how the hemoglobin traveling through this capillary picks up it and becomes saturated as a function of its PaO2, and the saturation of hemoglobin contributes to the majority of the O2 content, the amount, the actual volume of that oxygen carried by hemoglobin, driven by the PaO2, it's got to be lower. So there's lower O2 content being contributed to this one, normal O2 content being contributed by the normal units, and I put in quotes, higher oxygen content contributed by the high VQ units. So why doesn't all of this balance out? Why don't we have low units, underperforming, we have high units, we have higher performing units, we have normal units. Why doesn't it all balance out? And you all heard the answer in Amy's lecture. And that's because, well, two reasons. One, first of all, we've just defined that these are units getting less blood flow. So there's just less of this contribution from these higher units. But much more importantly, the incremental increase in oxygen coming from these units, the incremental increase not in PaO2 but oxygen content, is relatively small because we're operating on the flat portion of the oxygen hemoglobin dissociation curve. So here, this is a almost maximally saturated set of hemoglobin. Okay? We drive up the PaO2 to 132, you don't get it's flat. You don't get any more oxygen content, or only a tiny little bit. You've jacked up that PaO2, but all the buckets are full. You can't carry any more oxygen. So the contribution from these higher performing, these high VQ units, doesn't add incrementally much oxygen to the blood. Okay? It is the fundamental lesson of oxygen content. Once you've saturated your hemoglobin, trying to jack up that PaO2 doesn't matter. Okay? So in a sense, we've set up a scenario where these low VQ units are dragging down. If all of these units are contributing blood to the final pool, these low VQ units are dragging the final mix, the final amount of oxygen in the blood down. Okay? And that's compared to the just overall PaO2. These units contribute more. And again, we're not talking about disease, we're talking about the normal, healthy lung and the consequences of just normal physiologic VQ mismatch in the lungs. So what about PCO2? What's going on with PCO2? Is that affected in the same way? Well, the answer is no. Okay, so these are that same exact numbers. We already said that this unit can't overperform because it's operating on the flat part of that oxygen hemoglobin dissociation curve. Carbon dioxide is not affected in the same way. The dissociation curve is much more linear for carbon dioxide, so this unit actually does get rid of carbon dioxide to match the deficiencies in carbon dioxide removal from the lower unit. So VQ mismatch matters less. In fact, it doesn't really affect PCO2 until VQ mismatch is absolutely, absolutely dreadful. We haven't really gotten to disease. We're talking now just about normal lungs. But that physiologic mismatch doesn't affect PCO2. Your PCO2 in your blood, we've talked about it in many different lectures, the PCO2 in the blood and the PCO2 in the alveolus are essentially the same. Okay. So what is the net effect of this physiologic mild VQ imbalance in the normal lungs? Amy alluded to it and hinted with her patients, the 3 patients that we had in the end of the last lecture. All right, so VQ matching was absolutely perfect, and there was none of this little physiologic VQ mismatch in the lungs. We would have this alveolar concentration of oxygen, and if diffusion was perfect, let's just assume that it is, we would have, when we measured a person's radial artery gas, we would see that everything's perfect, ventilation perfusion matching is dead on VQ of 1. We would measure a PaO2, a P little AO2, an arterial concentration of oxygen that was the same as this alveolus. But what we find is that that's not the case. We know that the PaO2 is, as a result of this physiologic mismatch, dragged down a little bit relative to what it would be if the VQ matching were perfect. So we call this ideal PaO2, and we calculate it using the alveolar gas equation. So how much is the final blood mix dragged down by this little bit of physiologic matching? We can measure it. And the way we measure it is with a radial artery stick or a femoral artery stick and a blood gas and the alveolar gas equation. Okay? The alveolar gas equation is actually not as difficult to memorize. For the most part, this is going to work out to be 150. This is 0.8. You're basically measuring one value. It's a really simple equation to commit to memory. And again, we're going to use, just like Dr. Atkinson did in her lecture, the PCO2 from an arterial blood gas to calculate what this person's ideal PaO2 would be. And then we're going to look at the P arterial oxygen and see how different it is. Okay, does that make sense? Okay, and again, if you're falling behind or you're not caught up, you're going to see this played out over and over and over again in the next bunch of slides. Okay, so again, to be repetitive, an arterial blood gas is going to give us a patient's arterial PCO2, their arterial PO2, the P little AO2. We can use the arterial gas equation and this number, or the alveolar gas equation and this number to calculate that ideal expected PaO2, and we can see the difference. And we call this thing the AA gradient. Okay? Now, again, we're focused on normal, healthy people. Okay? So this is the identical blood gas that was drawn, I think, in one of your patients. We draw a blood gas. This person is absolutely healthy. They're feeling fine. We find that their pH is 7.4, their PaCO2, because it's the same as their alveolar big A CO2, we just call it PCO2. But their PCO2 is 40, and their measured concentration of oxygen in the blood is 90. Okay, so now let's use this PCO2 and the alveolar gas I call it. I make this mistake actually speaking all the time. This is the alveolar gas equation, not the arterial gas equation. But, all right. So we know that PiO2 is a function of the atmospheric pressure minus the water pressure times 0.21. And PiO2 then becomes 150. Let's plug in our 150 and our measured PCO2. And we find that the ideal PaO2, given this PCO2, should be 100. And we've already measured what's going on in the blood. So what is our AA gradient? Our AA gradient is 10. All right? So a normal, healthy person has a gradient between what should be in their alveolus, ideally, and what we see in the blood. And the answer as to why that is because of this physiologic VQ mismatch. There's a range of alveolar units with a range of VQ relationships, range of lung units with a range of VQ relationships, and the underperforming, the low VQ units drag down the final blood oxygen concentration a little bit. All right, now that's a little bit of an oversimplification. There are a couple other reasons why we get an AA gradient in a normal healthy person of 10. As Dr. Atkinson said, diffusion isn't absolutely 100% perfect across the alveolar capillary membrane. There is a tiny little bit of shunt flow, and we'll hear more about shunt flow in a second, but there's some veins that actually never make it to the lungs and actually bypass the lungs completely and dump a little bit of deoxygenated blood back into the final pool. There's some bronchial arteries that do the same thing. But for the most part, let's just think about this AA gradient in a normal healthy person of 10 as being a function of VQ, physiologic VQ imbalances in the lung. Okay. So I do want to throw out here just a small comment, because you'll hear about it in some disease states. The body tries to compensate for this, and it compensates for it by this thing called hypoxemic vasoconstriction. And basically, the blood flowing to those low VQ units, the body can sense that the PaO2, the P alveolar concentration in those alveoli of oxygen are low, and the lungs constrict those blood vessels a little bit. Okay? All the blood vessels running to a particular lung unit run through other alveoli, and it can sense sort of what is the environment, and it tries to limit the blood flow to those units. So you hear about hypoxemic vasoconstriction as sort of a compensatory mechanism. But the bottom line is that a normal, healthy person is going to have an AA gradient of about 10. All right, so now let's move on to disease. And what I'll throw out, and I've mentioned before, VQ mismatch problems, worse than what we see physiologically, is a cause of hypoxemia in almost every lung disease. Okay? And that's because lung diseases, particularly parenchymal lung diseases, but also airway lung diseases, can affect ventilation, they can affect perfusion of the lungs, and they can affect both. All right. So Dr. West did that same measurement of lung units and what their VQ relationship was in patients with disease. And so here's a patient with chronic bronchitis, and they have some areas of their airways that are very, very inflamed, and that's reducing ventilation to those areas. And what we see is there's this population, there's some normal lung in this person, but these population of lung units that are getting good blood flow, but really crummy ventilation. They have low VQ relationships. And here, in this actual measurements of an actual individual patient, there are some lung units that have a VQ relationship tenfold away from normal, the VQ of 0.1. Okay? Let's assume 1/4 of all of this person's lung units. Sort of looks like that could be the case based on the size of those curves. And let's say that based on the degree of extreme hypoventilation of those units, that their PaO2 is 50. P alveolar concentration of oxygen is 50. And if you go back to that red line, 50 matches out fairly nicely with one of the possible alveolar concentrations of oxygen and carbon dioxide. So let's say this person now has a collection of these low VQ units, 25% of them, and a bunch of normal lung, and now we look at what happens to the final blood mixture when these units contribute their blood. The PaO2 has to go down. Okay? This is contributing normal oxygen content to this pool. This is contributing reduced oxygen content to this pool. The final mixed pool of blood has to go down. The low VQ units in this particular patient drive down the final measured arterial concentration of oxygen in the mixed blood. So VQ mismatch, that's all it is. And we see VQ mismatch in all kinds of diseases. This is a person with fairly severe pulmonary fibrosis, sort of normal lung tissue here. If you look outside here, all of this diseased lung has capillaries running through it, but very, very poor ventilation. This is a patient with acute hypersensitivity pneumonitis. You don't need to know what that is. You can just see that their lungs are very, very inflamed, and they have a lot of low VQ units. They might have some high VQ units, but the low VQ units are what dragging down this person's final concentration of oxygen in their arterial blood. I have no idea what this person's disease is, but it's something bad. Here's some abnormal lung VQ mismatch. Now, you can have diseases with VQ mismatch in the other direction as well. This is a person with emphysema. They have some scarring here, but mostly it's just a lot of black. They have a lot of destroyed lung tissue. There's no capillaries in this big bunch of air. They're going to have a West diagram that looks like this, with some areas that are getting a lot of ventilation but no perfusion. This person has an abnormality, but it's not going to be a hypoxemic abnormality. This person's wasting a lot of energy moving air in and out, moving gas in and out of these regions of lung, and that's bad. We call that wasted ventilation, but it's not specifically, at least in this one patient, causing, or has the potential to cause hypoxemia. All right, so we're going to move on to some additional concepts. We're going to look at this AA gradient in VQ mismatch. Now, you have all of the information to figure out that the AA gradient is going to go up, okay? The alveolar concentration difference that we're going to see in the arterial blood versus what we calculate for the alveolus is going to go up, okay? And that's because when we measure the big A, O2, when we measure ideal, we're going to measure it based on carbon dioxide. And carbon dioxide isn't affected by VQ mismatch. So it's going to tell us what should be there in that alveolus. And we'll measure what finally ends up in there in the arterial blood. So VQ mismatch and the AA gradient. We know that VQ mismatch lowers the arterial concentration of oxygen in the mixed blood. We know that it doesn't have an impact on PCO2, so we can use that PCO2 to calculate an expected and ideal PaO2 and measure the difference. The one thing I'll mention now, in response to hypoxemia, you might hyperventilate to try and, your body wants to drive up that oxygen if it can. So you can actually drive down the PCO2 with hyperventilation. So PaO2 might actually be high when you calculate its ideal. And then you measure what's going on in the blood, and you find that it's being dragged down by these low VQ units. Okay, so let's do a couple clinical examples. So we have a 71-year-old man brought in by ambulance. He's short of breath. He's had labored breathing for an hour, say. He has a respiratory rate that's high at 28. Saturation's 90%. And you draw an ABG. He has a pH of 750. He's hyperventilating a little bit. He's driven down his PCO2, and this is what you measure in his arterial blood, a PaO2, a arterial O2 of only 62. What is his AA gradient? Okay, so oxygen's low. We calculate using this carbon dioxide level what his ideal PaO2 would be, and we get a alveolar concentration of oxygen of 110. So he has an enormous AA gradient. Okay. The ideal alveolar concentration of oxygen in the context of what we see with his hyperventilation is high. What we actually measure is much, much lower. We know normal is 10, so he has a tremendous AA gradient. Okay. Gas exchange is impaired. Now, okay, and possibly VQ mismatch is the reason. I will say there's a good chance that VQ mismatch is the reason because it's the most common reason for hypoxemia. We know that this is not the reason. He's not having alveolar hypoventilation. We already said he's hyperventilating. So maybe VQ mismatch is the reason. So just to summarize, VQ mismatch is a cause of hypoxemia, and it causes an increase in the alveolar, in the AA gradient. Okay, so let's go back to those extremes of VQ mismatch. So here is a lung unit that is not getting any ventilation at all. VQ is 0. Here is basically a lung unit that is getting ventilation but 0 perfusion. VQ is 0 and infinity. And we already said this is essentially dead space. All right? And this is a scenario that we call shunt. Okay, now we talked at the very beginning that there can be shunt going, bypassing the pulmonary circulation through cardiac or larger vessels. But here we're talking specifically shunt at the alveolar level. We have absolutely no ventilation coming to this alveolus. So does that happen? Yes, absolutely. So let's fill this alveolus up with fluid, okay, in pulmonary edema. No gas exchange is happening in this alveolus. Ventilation is 0. And the final concentration of oxygen at the end of this capillary is going to be the same as venous blood. Okay? So shunt. Shunt drags down the final mixed, measured arterial concentration of oxygen and has to therefore elevate the AA gradient. Okay. Shunt is this extreme form of VQ mismatch. And like I said, it's basically just deoxygenated blood that never picks up fresh O2 mixed in with the final blood pool. And it can occur in the heart as well. Right to left shunt, if you have very high pressures in the right side of your heart, can give you the same bypassing of the pulmonary circulation, deoxygenated blood at the alveolar level, at the macro level, added to the final blood pool. Okay, does this occur? Absolutely. So here's a person with pneumonia getting a contrast scan. So this is his, left pulmonary artery, pulmonary arterial blood flowing into this pus-filled area of lung. That's shunt. All this blood flowing in all these little white lines is not picking up any oxygen. It's added to the final mix. So this is a person who has a fairly bad pneumonia, but he has all this other normal lung. His arterial measured oxygen concentration is going to be low because he's shunting deoxygenated blood through that abnormal lung tissue. Okay? So does VQ mismatch affect PCO2? Not so much. And that is because, as I alluded to a couple slides ago, the body can hyperventilate to affect PCO2 and make up for deficiencies with these well-ventilated units. So here we have a scenario where actually, I think if you're following along at CourseWorks, I changed this number just a little bit to make it a little bit lower, and I'll post a corrected slides after this lecture. But I think in the thing that's on CourseWorks, I have this at 50. It should be a little lower. These are dragging down the PCO2. These are dragging down the PCO2. We have the whole alveolar setup such that this person has an elevated blood PCO2. Now, what happens? The body senses that, says, I have to fix this, and it hyperventilates. And that hyperventilation, this is an underventilated unit, so it's probably not going to affect that too much, but you're going to ventilate this a little bit better, and you're going to ventilate this a little better, and you're going to drive down PCO2, and you're going to normalize the situation. So a little bit of VQ mismatch affecting more than physiologic, pathologic VQ mismatch affecting PCO2 gets corrected very, very quickly by the body and the chemoreceptors in the brain to correct it with these higher VQ units. The problem, though, is that takes work. And we see this in a variety of lung diseases where VQ mismatch or other problems are causing PCO2 to be higher. The body corrects it by hyperventilating, but that takes energy. All right? This is just a variety, a series of blood gases from an individual patient who's starting out normal with a measured concentration in the blood of 90 for their oxygen, and PCO2 is 40. Everything's normal. We give them a disease with VQ mismatch, and their PaO2 goes down. Their PaO2 goes up, PCO2 goes up, and then the body senses this and hyperventilates. We already said that hyperventilation probably is not going to affect this very, very much because we can't improve oxygen by overventilating those high VQ units. Oxygen's already supersaturated coming out of those units, but we can fix PCO2. So we see this scenario in a patient with bad lung disease where they walk around hypoxemic when you measure their blood gas, but their PCO2 is actually normal. until this person starts to get tired. And they can be tired chronically, they can be tired acutely, and if they can't spend that energy to hyperventilate, things go back to the pathologic state. Okay? We call this respiratory failure, but the honest truth is this is the system is failing here. This is VQ mismatch at work, and we see it because of the low measured oxygen concentration in the blood. So this is potentially respiratory failure, but we label this when the PCO2 starts to rise as respiratory failure. All right, so, and there are other causes of respiratory failure as well. So let's look at just a few other causes of hypoxemia. All right. You've heard in various lectures about diffusion abnormality. I leave this to the end because there's a tendency for people to assume anytime we're talking about an AA gradient, we're talking about a pure diffusion problem. Or when we talk about, in a few slides, the diffusing capacity of carbon monoxide, a test that we measure, we think, oh, that's just gas is having trouble getting across this membrane. All of these membranes I've shown up to this point have been normal. It's all this mismatching of ventilation perfusion that are driving the problems with gas exchange when we look at the lungs globally. Now we're going to talk very specifically about a patient who has diffusion problem. Let's just go right to the patient. These are normal alveoli. This person has interstitial pulmonary fibrosis. There's a lot of scar tissue in the space between their alveoli and their capillary. Look at this sad little alveolus that's got to get its oxygen through all this junk in here. Okay? This person's going to have a true diffusion abnormality. Now, you saw this slide in Dr. Atkinson's lecture. This is the normal transfer of oxygen as blood is moving across the capillary. A hemoglobin molecule in a red cell enters the capillary. It has 3/4 of a second to pass through it, and oxygen is equilibrating almost all the way up to 100% equilibration relatively quickly. Now, this person in that slide that I showed you has all this scar tissue in their lungs. Oxygen is going to have a harder time getting across. And it may not, by the time that red cell leaves that capillary, have picked up all of the oxygen that it can pick up. Okay? This is a diffusion abnormality. And the reason is that the movement of that gas, you saw this equation a lot, is a function of the surface area, but the thickness matters. Okay? Increasing the thickness is going to reduce the movement of that gas. All right. The important thing to hammer home, and the reason that I leave this to the end, is that this, for the majority of patients, is a relatively minor contribution unless disease is very, very severe. Even in the patients who have interstitial lung disease, it's something that fills up the interstitium, the majority of those patients have problems related to VQ matching as the cause of their hypoxemia. But diffusion abnormalities absolutely can come into play, particularly when diseases are severe. I'll tell you, this is pretty severe pulmonary fibrosis. Okay. If you think about it, gas will be normal in this alveolus. It will be reduced as a function of this thickened membrane. This ratio, this gradient, is going to be high. Diffusion increases the AA gradient. It has to. Okay. Same as we talked about earlier. There's this D in the AA gradient. Don't think of the AA gradient as a measure of a diffusion problem alone. It is a measure of gas exchange. And VQ mismatch with a perfectly normal membrane is going to raise the AA gradient. Diffusion raises the AA gradient, but don't think of them as exactly the same thing. If you see a high AA gradient, it could be diffusion. We just learned that. It could be VQ mismatch. And it could be shunt, right? So one final cause to talk about before we sort of sum up all the reasons why somebody can be hypoxemic. We talked about, before we get there. So you can have a diffusion problem that exists primarily with exercise. Let's look at this person here. They have at rest a alveolar calculated using the alveolar gas equation. Their alveolar concentration of oxygen is 108, and we exercise them, and it goes up to 115. Why did it go up? Because their carbon dioxide went down. They're hyperventilating with exercise, and that's good. Okay? But look what happens to their measured oxygen concentration in their blood. It actually goes down, and their AA gradient, which was abnormal to start, suddenly goes up. Why is that happening? It's because blood is flowing much faster through their capillaries. So here's this person who's abnormal to start. Now they're exercising. This is the only space that this distance here, the hemoglobin has to pick up oxygen, and then it's out of the capillary. Okay? A normal person doesn't really hit that spot because they've equilibrated early. You take a person who's just mildly abnormal, they can have a normal measured oxygen concentration in the blood, but then abnormal with exercise. In this graph, this person's a little bit abnormal and becoming much more abnormal as they exercise. This diffusion problem is exacerbated by exercise. So one final cause of hypoxemia is obviously a low inspired oxygen, and we see that at altitude. These are different locations than was in Dr. Atkinson's slide, but I live in Ocean Grove, New Jersey, just a little bit above sea level. If you're in an airplane cabin at altitude, your PiO2 goes down because P atmospheric goes down. And as a consequence, what you see in the blood goes down. Breckenridge, Colorado, I didn't calculate it out, but it felt somewhere close to the peak of Everest. This is your measured oxygen concentration in a normal person's blood on Everest. And the body needs what it needs. The body's going to take what it can get out of there, and if that's sufficient, what's coming back to the heart in those capillaries is going to be very, very, very low, minus what the cells have needed. But that's a scenario with a low atmospheric pressure causing a low PiO2, causing a low measured O2 in the blood. Okay? But gas exchange is completely normal in those people. The A gradient is going to be normal. Okay? So this is the summary slide. I put a little red star here. This is a memorized for the exam graph. These are the 5 causes of hypoxemia that we've talked about in Dr. Atkinson's lectures and mine. Alveolar hypoventilation, all by itself with normal gas exchange and a normal AA gradient causes hypoxemia, as does a low PiO2. And then all of these 3 things cause a high AA gradient. Impaired diffusion, the last thing we talked about, right to left shunting, which we talked about before that, and a low VQ. All of these things are going to elevate the AA gradient. Okay. Important thing to remember, though, is that patients don't just sometimes have one cause for their hypoxemia. More than one thing can be going on at the same time, and it's your job to sort it out. And we have, as the way to sort it out, the alveolar gas equation. Okay, so we can, I'm sorry, I'm going to fix this. Alveolar gas equation. It's like a mental block that I have. It is the alveolar gas equation to sort out causes of hypoxemia. Okay, if a patient has a high PCO2, one of 2 things is going on. Either alveolar concentrations of oxygen have gone down because the patient's hypoventilating, or they've gone down because the patient's hypoventilating and something else. Okay? It's that simple. We know they're hypoventilating. Their PCO2 is high. Either that's the only problem or something else is going on. So how are we going to tell the difference? We know that hypoventilation by itself doesn't cause the AA gradient to go up. Other things do. If we calculate an AA gradient in a patient and they're hypoventilating and the AA gradient's high, you've discovered 2 problems affecting their oxygen. Okay, so let's just play that out in a couple examples. Here's a 55-year-old woman brought in by ambulance with shortness of breath. She's saturating low. Her pH is 7.2. Her carbon dioxide is 64. Her oxygen is 58. What can we tell about her hypoxemia? We calculate an AA gradient, and it's normal. Okay, you can go back and look at the equations. Her AA gradient is normal. So gas exchange is normal. The only cause for hypoxemia in this woman is that she is hypoventilating. Okay, let's do another person. Their pH is 7.3. Their PCO2 is 50. The PaO2 is 62. This person is hypoventilating. We know one cause for their hypoxemia is the fact that they're hypoventilating. But we calculate an AA gradient, and we see that their ideal in the context of this PCO2 should be 87.5. It's not. Their AA gradient is 25, 15 above normal. This person has hypoxemia for 2 reasons simultaneously. Their PCO2 is high and they're hypoventilating, and they have some impairment of gas exchange, probably VQ mismatch. Okay, so can supplemental oxygen fix these scenarios? The answer is sometimes yes. If somebody is hypoventilating, every incremental increase in your PiO2 is going to increase your PaO2, and that's going to improve the problem. Okay? Hypoventilation and hypoxemia, we can fix the hypoxemia relatively easily by putting oxygen on a person. Supplemental O2 and VQ mismatch, does that improve the situation? Absolutely. So you put 100% O2, a mask on this person's face, their normal units increase, and the abnormal units increase. Now this is an underventilated unit, but it's still ventilated. Eventually oxygen is going to increase in this alveolus. It might not be immediate, it might take some time, but oxygen concentration in this alveolus, the abnormal lung unit is going to increase. Your blood concentration of oxygen is going to increase. Okay? So does it improve it in a diffusion? Absolutely. So here's the movement of this gas. It's affected by this gradient. We're going to improve oxygen and improve this gradient. Oxygen improves the hypoxemia of diffusion. Sorry. How about supplemental oxygen in shunt? Contrast that with the last slide. This is the abnormal contributing lung units. This lung unit's filled up with pus. Is supplemental oxygen going to fix that situation? Absolutely not. Okay? You just can't impact the abnormal units in shunt, so all the oxygen in the world is really not going to improve the oxygen in a person's blood. Now you say, well, what about we've driven the PaO2, the alveolar concentration of oxygen, up to 650 here. Doesn't that jack up the PaO2? Absolutely. But we already learned that what matters is oxygen content. This doesn't help. We're all the way up on the saturated portion of the oxygen hemoglobin curve. Now, Dr. Atkinson mentioned you can use shunt and 100% oxygen, the phenomenon of shunt, to actually measure and even quantify how much shunt is going on in a patient. You give somebody 100% oxygen, and we're assuming that there's a little tiny bit of shunt. That contribution of shunt flow is going to drag down the final measured oxygen concentration in the blood. Even if it causes the desaturation of just a couple percentage points, you see the PaO2, which is on this x-axis, drops all the way. So very tiny shunt dropping the saturation just a tiny little bit will drop your PaO2 from what you expect it to be in the many, many hundreds down to under 200 in this example. So you give somebody who may or may not have shunt 100% oxygen, you expect to measure, if everything's going fine and there's zero shunt, you expect to measure an arterial concentration of oxygen that's 600 something, and you measure and it's 200 something, you know there's shunt there. Okay. So I'm going to end with, we're just going to go 1 or 2 minutes over, with one of the ways in the pulmonary function testing laboratory that we measure gas exchange, and that's with diffusing capacity. We know that this is the equation of how gases move across a alveolar capillary membrane, or any membrane for that matter. The surface area and the thickness, are the characteristics of that membrane. These are the characteristics of the gas. You can look at the characteristics of that membrane as how a particular gas behaves. And in particular, we're talking about the alveolar capillary membrane. We can use a particular gas at a particular concentration and judge essentially the health of this membrane. How good is its surface area? How good is its thickness? Okay. And we want to look for a particular gas that we can use as a test gas. When we apply a test gas, a gas that we know is at a particular concentration. We know the properties of that particular gas, and we measure the flow across the alveolar capillary membrane. That final measurement is what we call the diffusing capacity, or the diffusion capacity of that gas. Okay? And that, as I said, tells us about the health of that membrane. So if we want to pick a gas, what gas are we going to pick? We want to pick a gas that has some diffusion limitation. We don't want a gas like carbon dioxide that diffuses so easily that it doesn't really tell us anything about the membrane. We want to measure something that's not already in the blood so that we can see how it's moving into the bloodstream from the alveolus without having to subtract out what's already in the blood. And we want something that's non-toxic at low doses. Believe me, this is actually carbon monoxide. At low doses, carbon monoxide is very non-toxic. The diffusing capacity of carbon monoxide we measure as the rate of transfer of carbon dioxide after we give somebody a low concentration to breathe, the movement of that carbon monoxide into the blood at a known partial pressure in the alveolar space, and we can measure the health of their alveolar capillary membrane. You don't need to learn this. This is just how we administer carbon monoxide to a patient in the DLCO maneuver. And we basically measure how much carbon monoxide went in. We measure how much came out. The difference is how much went into the blood. We can use the change in the concentration of what's blown out to determine what was the concentration in the alveolus, and we get a DLCO. Now, a lot of diseases affect the DLCO because they affect that surface area and they affect that thickness of the membrane. Emphysema, interstitial lung disease, pneumonia, pulmonary edema, all of these things will reduce your DLCO. If you just have pure asthma and you're not VQ mismatching terribly, your DLCO should be normal. Just like the AA gradient, the DLCO looks at gas exchange. It's not just, diffusing is right there in the name, but it's not just talking about diffusion. Lots of other things affect it. So emphysema with decreased surface area, lots of lost alveoli will lower the DLCO. If you're anemic and you just don't have as much oxygen carrying capacity, you'll have a low DLCO. And then severe VQ mismatch will affect your DLCO as well. You can see a low DLCO in carboxyhemoglobinemia and some pulmonary vascular diseases. And then strangely, you can even see a high DLCO if somebody has a lot of extra blood volume, as is the case with obesity, and in the case of left to right shunting. Somebody bleeds into their alveoli, their DLCO will be artifactually high, taken up by all the hemorrhaged blood. DLCO is an imperfect test for a variety of reasons. It's reduced in a lot of different lung diseases. Even if the DLCO is normal and a person's hypoxemic, VQ mismatch is most often the cause, irrespective of what you see. Gas exchange is impaired in a patient with VQ mismatch, even if the DLCO is normal. So I'm just going to end very quickly with one last physiologic principle, and that's the issue of carbon monoxide poisoning, because it's interesting. These are things that Dr. Axelson talked about that shifts the oxygen hemoglobin dissociation curve to the right. That helps us unload oxygen in the tissues. She talked about that, so I'm going to skip over it. Carbon monoxide is a thing that's present in the blood, particularly in smokers, in very small amounts. And heavy smokers can get up to 10%. But it is the single most common cause of poisoning in the United States and a high top 10 cause worldwide, mostly related to breathing in either accidentally or volitionally of exhaust fumes. The reason that it's very, very toxic is that it binds to hemoglobin with this huge efficiency. It's 200 times the affinity of oxygen, so it displaces all of this oxygen from hemoglobin. So you can't carry oxygen on hemoglobin that's already carrying carbon monoxide. And it shifts this dissociation curve in the other direction. It makes it very hard for the oxygen that's there to get off the hemoglobin molecules. The problem is it doesn't do anything to dissolve oxygen in the bloodstream. So if you measure a blood gas in somebody, their measured oxygen concentration, which is a p(a)O2, it's dissolved oxygen, it's going to be high. If you give them 100% oxygen, it's going to be 600, but the person's dying of hypoxemia because of carbon monoxide poisoning. So you have to be very careful and in the right clinical context suspect carbon monoxide poisoning if the patient's been exposed. Because carbon monoxide elimination is related to the half-life of carbon monoxide, and the half-life of carbon monoxide changes depending on how much oxygen you give somebody. Giving somebody 100% oxygen helps get rid of the carbon monoxide. Giving somebody hyperbaric oxygen, oxygen at a higher partial pressure in a hyperbaric chamber, gets rid of carbon monoxide very, very quickly. So that's actually the recommended treatment for carbon monoxide poisoning if it's severe and causing symptoms. So I'm going to end there. Sorry for running a little bit late. Do we know what their next? So I'm going to have, if anybody has questions, you can come up afterward, but email me if you have questions as well. And I thank you very much. It's been sort of a whirlwind of gas exchange, but we hope it makes a little sense.
Hi, Janice.
Yeah, they haven't had it.
I make a quick announcement?
Sure,
There's no
quick.
problem. So just a quick announcement. Somebody just informed us that the PDF in CourseWorks for some of these lectures is showing the equations as missing some symbols. So we're going to have Betty, if she can, post the actual PowerPoint files for these particular lectures where they should all be accurate. So look for that later today, and we apologize for the mistake.
Is this some of the
Yes.
pictures here?
Yeah, I have a question.
Sure.
Could you explain to me once again why 100% oxygen doesn't help when you have that shunt?
Yeah, so basically, I draw on the back of that?
Yeah.
Okay. Basically, at its most essential, you have two populations of alveoli, an abnormal and a normal, and the mix of those two is dragging down arterial oxygen, right?
Yeah.
If you give 100% oxygen, you can't make this alveolus any better. Just oxygen doesn't get there. There's no gas exchange. This shunt keeps going.
Right.
So this is going to have a low O2 content. Okay? Here, obviously, 100% oxygen, you're going to jack up the PaO2 super, super, super high. Okay? So let's say our PaO2 is 600. Okay? But what matters is O2 content. So we have hemoglobin at a PaO2 of 120. This hemoglobin's all full. It can't hold anymore. Okay? So all you're adding is just a teeny little bit of dissolved oxygen. Even though this is a lot of dissolved oxygen relative to this, it's a tiny, tiny, tiny little fraction. 0.03003, I think, as much oxygen is here. So you've added this little tiny bit of dissolved oxygen. You have all this unsaturated hemoglobin
So
coming
essentially,
through here.
that unsaturated hemoglobin could not be used here. It's
It
not.
can't. Once
because-
we mix this pool with saturated hemoglobin and unsaturated hemoglobin and a tiny little bit of dissolved oxygen and more dissolved oxygen, this just gets sucked up by a tiny little bit of this, and all of this desaturated oxygen, desaturated hemoglobin mixes into the final pool. Yeah.
Oh, it's oxygen. I see.
Okay.
Okay. Dr. We're on left.
just tell actually. Yeah.
Would like to get started, please. Okay, so the topic I'm going to talk to you about is anxiety disorders. My name is Frank Schneier. I'm in the psychiatry department here. And the core of anxiety disorders is what we're really going to cover. These include panic disorder, several different phobias we'll talk about, social anxiety disorder, and generalized anxiety disorder. These are my disclosures. So we're going to talk about the symptoms of these disorders, how to recognize them, some ideas about the etiology of these disorders, what are the various physiological or psychological factors related to these, and clinically how to differentiate these disorders and diagnose them. So fear and anxiety, we're all very familiar with having experienced, but they also have some technical aspects to their definitions. While they seem uniquely human, they're also really human versions of something seen across all biological species of mechanisms for withdrawal from aversive stimuli. And fear and anxiety refer to slightly different things. Fear is more the emotion related to an immediate response to threat. So when you're attacked by a lion, that's what happens. You mobilize for either fleeing or fighting. Whereas anxiety is more future-oriented. It's emotion related to the anticipation of threat. And so that, if it's being, it should lead to useful behaviors like preparing for the threat or avoiding the threat. So anxiety disorders, though, are characterized by excessive anxiety or inappropriate anxiety that occurs when there's really no threat or not a serious threat. As a group, the anxiety disorders are the most common of psychiatric conditions. They affect more than 20% of the population in terms of lifetime prevalence. And they're quite costly in terms of missed work opportunities and cost of care. These are very old numbers. I'm sure they're many times greater since 1994. Historically, anxiety disorders are relatively new kids on the block. They got separated out from depression symptoms in writings in the 18th century. Freud talked about anxiety neurosis, which really overlapped these disorders that the modern terminology has been established since about the late 1970s with DSM-3. And at that point, these disorders were separated out based on several clinical features. One, the syndromal coherence. What symptoms seem to co-occur in people? What's the characteristic course, the age of onset, the course over time? The pattern of comorbidity, what other things co-occur with these particular symptoms, and which symptoms tend to be familial, to be shared within a family. So based on these clinical observations, these disorders were differentiated. And as I mentioned, we're going to talk about the ones listed here in white: panic disorder and agoraphobia, which often co-occur. Specific phobias, there are several subtypes of these we'll talk about. Social anxiety disorder, which has also been called social phobia. Generalized anxiety disorder. And then there's some other anxiety disorders I won't talk about today. Two in yellow are the separation anxiety disorder and selective mutism, which are commonly occurring more often in children, and were just recently added to the adult categories in DSM-5. And then a couple of disorders that you'll hear about in other lectures, or you've already heard about, I believe, PTSD and obsessive-compulsive disorder, which historically were thought of as anxiety disorders, but have some different characteristics that have caused them to sort of straddle. Sometimes they're called anxiety disorders, sometimes they're called something a little different. Just in terms of frequency, lifetime prevalence here, you can see a number of anxiety disorders compared to the most common of psychiatric disorders, depression and alcohol dependence. And in this nationwide community survey from the 1990s, you can see social anxiety is quite common. Generalized anxiety disorder somewhat less, and still pretty high rates for panic disorder and OCD. So we've grouped these disorders together because they have some similar characteristics. So let's start with what they have in common. For all of them, anxiety is a central kind of feature. And all these disorders also tend to have an early age of onset, most commonly in the teens or early 20s, though there's some differentiation by specific disorder. They're all more prevalent in women, typically by about a 2-to-1 ratio. They all can cause significant social and occupational disability, and they can lead to other problems. They are risk factors for depression, for suicidal ideation, or even suicidal behavior, and for substance abuse and often alcohol abuse. They all have treatments that are pretty well established with efficacy at this point, but they tend to be undertreated. People often don't seek treatment unless their condition is severe, or sometimes when they develop a secondary depression or other problem that will bring them into treatment. We'll talk about certain kinds of symptom clusters that can occur across these different conditions. So one is the panic attack. And a panic attack we define as a sudden onset of anxiety that peaks in the course of several minutes at the most. You have to have intense fear, and it's been operationalized as having at least 4 of a group of symptoms that can occur. So these include fear of dying, fear of loss of control, these kind of cognitive symptoms of negative thoughts, as well as physical symptoms, including palpitations, sweating, trembling, difficulty breathing or chest pain, choking, nausea or dizziness, derealization, the sense that things around you seem unreal, feeling spacey, paresthesias, or sensations of feeling hot or cold. Anticipatory anxiety, on the other hand, is a more chronic kind of condition, typically comes on gradually. It's about the future. This is worrying about the future. Phobic avoidance is also common across many different disorders, and we're talking about avoidance of a feared situation due to excessive or irrational fears about that situation. And often these syndromes are accompanied by physical symptoms of autonomic arousal. So these may include palpitations, increased heart rate, sweating, dry mouth, and they may vary in individuals within a disorder, and there's some physical symptoms that tend to be more likely to be associated with one disorder than another. So let's talk about each disorder individually now, starting with the criteria for the diagnosis. So panic disorder's hallmark is panic attacks. And they have to be both initially unexpected and recurrent. So it's not just having one, it has to be an ongoing issue. The person has to have persistent concern about additional attacks, that they may have bad consequences or that they may just suffer through additional attacks. And people have to have some change in their behavior. So it's an important event. It affects their future thoughts and their behavior. And it's not specifically due to some other condition or a substance, like marijuana can sometimes induce a panic attack. If it's only related to a specific situation like that, we don't consider it panic disorder, though it may have many similar characteristics. So sometimes people with panic disorder don't recognize their symptoms of anxiety. They recognize it as the physical symptoms and may present to emergency treatment for physical complaints, chest pain, fear of having a heart attack, fear of having a stroke. Sometimes patients get very caught up with the physical symptoms, and they may have difficulty accepting the idea that their symptoms are emotional or anxiety related, even if they've had a negative medical workup. So we have a videotape here I'd like to share with you.
What brings you in today?
I'm scared out of my mind. Something is going wrong. I'm breathing real fast. I'm hyperventilating. I'm just petrified. I'm going crazy. I've lost my mind. And I need some help right now.
When did you start having these symptoms?
I've had this happen before. I don't know what it is. One time when I was working on my thesis, I sat in the lobby working on it, and I thought I was going to go crazy, as if the walls were going to come down on me, as if I were going to scream, my head were going to come off. I felt, in fact, as if my persona were leaving my body. I was that scared.
Have you had any chest pain with this? Shortness of breath? Fast heartbeat?
I have these sharp pains right here, a tight squeezing feeling.
How long do they last?
Oh God, 5 to 10 seconds maybe, but when I had a real bad scare about a month ago, it lasted about a minute or two.
Does it go to your arm or your jaw?
No.
It's sick to your stomach, short of breath, fast heartbeat?
Well, short of breath sometimes. I feel like I'm hyperventilating when I get this scared. And it's like, can't get enough air. Oh, and the heartbeat, you said, yeah, I feel like it's pounding away. I feel like my heart is pounding so hard it's going to explode.
Do you have a history of any medical problems?
Not really. I'm really healthy.
Do you have high cholesterol or family history of heart problems?
No history of that stuff with me. My family is all alcoholics, so they all have that associated with their alcoholism.
Any history of blood clots, long trip recently, swelling in your legs, painful legs?
None of that stuff. I'm just freaking out. And I feel like my body's freaking out. The shaking and the breathing and the trembling and the sweats and the heart and the pain in the chest. That's what's going on. I feel like I'm going to have a heart attack or something, except I never do.
Any other medical problems?
I think, you get so confused when you're this scared. None, really.
Do you take any medicine? Do you have any allergies?
No.
Any chance you're pregnant?
None whatever.
Okay. I think it's important that I examine you to determine if there's anything new going on with you. Then I'll come back and talk to you and we'll get you some treatment.
So you might have guessed that patient is actually an actor. The doctor obviously is not an actor. But I think It illustrates the way people can present with physical symptoms, the need to do a careful kind of assessment as to whether there's any medical basis that needs to be addressed. And she gives kind of a full sense of kind of some of the ways people can present. So agoraphobia is a common phobic condition that, as I mentioned, it often occurs in people who are having panic attacks, though people don't necessarily have to have panic disorder in order to have agoraphobia. People with agoraphobia, it's defined as having anxiety about 2 or more of these conditions that are listed here: being outside of the home alone, using public transportation, especially if it's crowded, being in wide open spaces, being in enclosed spaces, standing in line, or being in a crowd. And conceptually, what these spaces have in common is that there are situations where somebody might have difficulty getting help in the event, for example, of having a panic attack or having symptoms that are scary. As in all phobias, it has to meet the criteria of the situation being avoided or endured with distress. In this case, people who have agoraphobia often feel more comfortable if there's some trusted companion nearby who could help them in some way or comfort them. And again, to meet the criteria, the threshold for a significant condition, the fear has to be excessive, go on for more than 6 months, and be impairing. Yes, so as I said, people with agoraphobia sometimes develop agoraphobia in the context of a panic attack. So someone will have a terrible panic attack, it'll occur in a crowded store, and they'll start avoiding that store, and then that can often generalize to avoidance of other crowded places, and people's lives can become very constricted and can be very impairing. So let's move on, social anxiety disorder. So the criteria for social anxiety disorder are the hallmark is a concern about fear of negative evaluation or being judged or offending others. And this results in a fear of a variety of social situations that range from performing situations like just giving speeches or being on stage to more generalized social situations, more informal social interactions, going to parties, speaking up in a meeting, interacting with friends in a group, or even one-on-one. So to meet the criteria, it's got to be a consistent problem. The feared situation's got to consistently result in anxiety. The person's got to either experience distress in those situations or actively avoid these kinds of situations. The fear's got to be out of proportion to the feared situation. So, yeah, if you're giving an important address before thousands of people, it's normal to have some anxiety, to be revved up for that. If it's part of your job and you're avoiding it and you're going to lose your job because of it, it's a different story. Or if you're feeling intense anxiety about talking with a friend because you're self-conscious about what they're going to think of you, again it reaches a threshold, becoming a problem. Social anxiety disorder sometimes can be associated with medical conditions that might draw unwanted attention, like a tremor. And if someone has a medical condition that's the focus of their social anxiety, the criteria designate that you meet the criteria for the disorder if the anxiety seems out of proportion to what would normally be experienced given that condition. There's reference in the literature to subtypes of social anxiety. Right now, the criteria designate just a performance subtype in which the social anxiety is limited to excessive fear about performance situations, meaning speaking in public, acting on stage. It could be other situations where you're just being observed, like eating in public and concerned that people will be watching you and notice that you're missing your mouth sometimes when you eat, things like that, or your hand is shaking. Most of the literature about treatment of social anxiety will refer to a generalized social anxiety disorder subgroup. And this is the more common form of social anxiety disorder among people seeking treatment. These are people who often do have performance fears, but they also have more general fears, so they're more self-conscious in many kinds of social situations. And if it really cuts across most social situations, then it's termed generalized social anxiety disorder. So I mentioned social anxiety disorder is one of the most common of the anxiety disorders. Here's a study we did a while back looking at age of onset. And in this study, and in most studies, you can see a mode age of onset in the mid-teens. That's when people are most vulnerable to developing this as a significant problem at a time when most people are having some increase in social anxiety and facing new stresses. And a subgroup of these folks also report having this as far back as they can remember. So when they were 5 and relatives were visiting, they would be hiding upstairs and avoiding interaction. And so, you know, if you make it, when I've made it to past medical school, it's unlikely to develop social anxiety after that age. Social anxiety disorder patients may also have some characteristic difficulties in interacting with medical professionals in general. Some of them avoid doctors due to the anxiety, the self-consciousness about having to talk about themselves, being physically vulnerable. They may look shy, have difficulty with eye contact, have a sweaty palm when you shake their hand. They may be self-conscious during a physical exam, and they may tend to be very agreeable because they don't want to create any conflict. But these are people who I think you need to follow up with to make sure they're really following through on what you've asked them to do and not just yesing you because they don't want to be a problem. And we've got another tape for you here.
Had difficulty with social anxiety probably from the age of 10 years old or so. Went to my pediatrician complaining of being nervous, age 10. He told me, I'm not nervous, not a nervous bone in my body, but if I thought I did have them, I would develop them. Not what I wanted to hear. What I wanted to hear was, oh, so that is what you're complaining about. Let's see what it is. Let's see what we can do about it. No such response. When I was about 15 or so, I started having difficulty with speaking in public. Speaking in public could be in front of 2 people, 3 people, 4 people, depending upon the degree of comfort that I had at that time. Similarly, saw a clinical psychologist, no assistance whatsoever. When I was 20, the symptoms started to add on, one at a time, seemingly out of nowhere. One day, I was at lunch with one of my colleagues, and I found that my hands started shaking when I was using utensils at a table. And I thought, I don't understand what's going on. And I thought it was a single episode. It wasn't. It continued to become more severe. Added to that, the next was glassware. Couldn't pick up glasses without having my hands shake. If I were a little bit older and a little bit wiser, as I am now, what I would have done is I would have said, gee, look at this, look at my hand is shaking, that's really something. And it goes under the caveat that I use of, if you can't hide it, flaunt it. And I just wasn't smart enough then. I'm a little bit smarter now, a little bit wiser perhaps with age and experience. So what I did was I tried to avoid situations that were uncomfortable in that respect. Next, I found that being with people in general became anxiety producing. I was afraid to take the trash from my apartment to the compactor room, lest I meet someone, one of my neighbors, in the hallway. So the trash went out at 3 a.m. when nobody would be there. Added to that, difficulty with handwriting. Didn't want anyone to see that I had a hand trimmer. So what I did was I had a presumably a good job, which I chose to leave to go back to school. Because in school, I had the ability to control what I did, when I did it. I was accountable only to myself. Symptoms continued to increase with regard to avoidance, so that during the latter part of the 1970s, I was virtually a hermit. I had friends, I had contacts, I had work that I could do, but I made sure that it was of the type that I could readily control and direct as I wanted to or needed to. I did.
Okay, so this fellow is not an actor. You may be wondering how we get social anxiety disorder patients to make a video to be seen by dozens of medical students. We treat them first. He had been through treatment, and he's interesting, I think, in he's very focused on the physical symptom of the tremor for him, which sometimes is seen. More commonly, it's not so prominent that there's a physical symptom, but someone may be just very self-conscious about the way they appear to other people, that they're going to embarrass themselves by not speaking fluently or showing signs of anxiety. So I mentioned before that social anxiety can interact with physical conditions that might draw unwanted attention, like essential tremor, stuttering, facial disfigurement, obesity even. And as I said before, that we think of these as people who have some additional factor like that that might draw unwanted attention, might cause certain people who might otherwise not reach a threshold of disorder of social anxiety to then kind of push them above that threshold. So the idea is you have some diathesis that might, for some people, make them more or less prone to social anxiety, and then certain stressors, whether it be developing a tremor or getting a new job where you've now got to speak to thousands of people, can bring you across the threshold where it becomes impairing and distressing. Moving on, generalized anxiety disorder. So generalized anxiety disorder is often thought as a kind of a worry disorder or a nervousness condition. So people have excessive anxiety across multiple events or activities. It's not limited to social situations as it would be in social anxiety disorder. People may or may not have panic attacks. Typically they don't have. That's not the focus of their problem. It's more worries about typical situations like family situations, worrying too much about their health, worrying too much about money, worrying too much about their safety. And the anxiety's got to be somewhat difficult to control. Again, there are specific criteria about having at least a certain number of physical or psychic symptoms, including feeling restless or keyed up, getting fatigued easily, having difficulty concentrating, being irritable, having muscle tension, and or sleep disturbance. Again, to meet the threshold, it's got to be either causing significant distress or functionally impairment. Specific phobias are a much more circumscribed condition, going from generalized anxiety, which is probably the most kind of broad, free-floating kind of anxiety condition, to specific phobias, which are very circumscribed about very particular situations. And the most common types of these include fear of flying, fear of particular animals, spiders, snakes, natural environment type fears like fear of storms, fear of water, fear of heights. And then something you'll see in our profession, blood injury fears, people who are afraid of the sight of blood, people who are afraid of getting their blood drawn, who avoid doctors because fears of injections and things like that. So again, to meet the phobia criteria, you've got to have a marked fear of a very specific object or situation. The fear's got to be out of proportion to the realistic danger of the situation. It's got to be a consistent problem, so it's not just a one-shot thing, but it provokes immediate anxiety. You've got to have marked distress or impairment. So if you're afraid of snakes, but you live in Manhattan and don't venture outside of Manhattan except to go to a zoo, you can't really make the criteria for this disorder. It's got to be something that goes on for a period of time. Now, again, not just a brief thing, at least 6 months is the convention. So even though these disorders can be very circumscribed, they really can be significantly impairing if people are avoiding medical treatment, for example, people who avoid flying, where that can be important for their work. So they're very focal, and they're thought of as the least severe in general, but they can also be impairing depending on the individual's circumstances. So let's move to talking a little bit about what we know about the causes of these conditions. And we know that they're heritable to some extent, that looking at families, each of these anxiety disorders tends to run in families. Individual disorders tend to breed true, so if you have social anxiety disorder, you're more likely to have family members with social anxiety disorder, more so than having family members with other anxiety conditions. Twin studies are the best evidence we have about the genetic heritability component, and ranging from here, well, it says 20 to 40, some studies even higher, up to 60%. So there's clearly some genetic component to the risk of developing these disorders. And there's also important contributions of environment, both shared environment, meaning familial environment, shared with other siblings, and unique environment of anything from life events to situations with peers. We don't know which genes are most important. It's clear that there's many genes that are involved, and each with very small effects. There's been quite a few neurobiological factors that have been identified as showing some differences in people with anxiety disorders versus not. Some of these have been found across different disorders, some specific. I'm not going to get into a lot of detail here, but just to give you a flavor of kind of what we know. Several neurotransmitter systems, the ones that we have studied the best and the ones that we have medicines that affect them, clearly are functioning somewhat differently in people with anxiety disorders. So these include serotonin, norepinephrine, dopamine, and GABA and glutamate systems. There are hypothalamic pituitary axis abnormalities in cortisol secretion and in central regulation of the HPA axis. Respiratory dysfunction it can be an issue, particularly in panic disorder. I know you just heard about respiratory illnesses. In panic disorder is the most common condition where people experience a lot of dyspnea. And there have been quite a few studies trying to understand that better, whether they have some differences in carbon dioxide sensitivity, and that does seem to be a factor. One method of studying panic disorder is inducing panic attacks by having people inhale mixtures of air that include higher levels of carbon dioxide than normal, and that can be panicogenic in people who are vulnerable to panic attacks. Other ways of thinking about this include animal models of fear conditioning. So the situation where one is exposed to a feared situation, let's say, in an animal will be a rat who's exposed to a shock in a feared situation, and that can lead to then fearing that situation in the future. And the natural course of fears is that we're exposed to feared situations. We might have a bad experience. I give a lecture last year, and I'm booed and off the stage, and it's terrible. But then I give a few more lectures, and it doesn't happen again. So I get my confidence back, and fear extinction happens. In other words, I've learned that I'm not generalizing from that one bad experience to all experiences. In anxiety disorders, it may be that people don't undergo that normal extinction process. When they experience a negative event, it may persist more and generalize more to other situations. It's also been noted that people with anxiety disorders may happen to have increased a bias towards attention to threat, so that we're all aware in the environment of potential threatening stimuli, but in laboratory situations, you can measure to what extent, for example, someone with social anxiety disorder might focus on an angry face out of a group of mixed happy and angry faces. So those kinds of negative stimuli may hold the attention more in people who are prone to anxiety disorders. And I mentioned, along with extinction, people may overgeneralize fears. So someone who's exposed, again, to one fear on, get stuck on a subway and they have a panic attack, they may generalize to all subways, to other crowds, to shopping centers, et cetera. Somebody else may just say that was a one-time deal. It's not going to be something I'm going to fear in other situations. And these are interesting because we do understand increasingly some of the neural mechanisms in animal models of some of these more complex behavioral issues. In terms of anatomy, we've learned a lot from functional imaging studies, particularly functional MRI, and there are many details, but the most, I think, a general way of thinking about this, we know that fear stimuli come in through sensory parts of the brain. They make their way to the amygdala, and the amygdala is a station where setting off the amygdala can lead to that fight or flight reaction, downstream effects, mobilizing the body. And it's clear that several frontal regions, the cingulate, the medial prefrontal cortex, naturally exert a down-regulating effect on the amygdala. So these control the activity of the amygdala. And in anxiety disorders, there's some process where either the amygdala is overactive or those cortical centers that control the amygdala are underactive. And that seems to be at least part of the process of what makes some people more vulnerable to more severe anxiety. As I mentioned, there's a genetic component, anywhere 20 to 60%, that leaves a big environmental component. So there are quite a few factors in the environment that may be important. They range from things like parental modeling. So if you have a parent who shows socially anxious behavior and is overprotective, you learn from that. Traumatic experiences. Some people who undergo a trauma don't go on to develop post-traumatic stress disorder, but they may go on to develop some other kind of anxiety condition, not uncommonly. People often develop anxiety conditions when they're under other kinds of stresses. Someone's just had a loss in their life. Someone has died, may be more prone to developing panic attacks, for example. And a variety of stressful situations can kind of, in people who are vulnerable, kind of push them above that threshold where they're having a problem. So switching gears a bit to some practical kind of clinical issues. How do you talk to a patient about anxiety and anxiety disorders? And there's some fairly simple kind of screening questions that can open the door as to whether someone has one of these conditions. You can just generally ask about if you had any problems with anxiety, worry, nervousness, any sudden attacks of anxiety or panic, any anxiety issues with people, and are you avoiding any situations due to fears? And this will cover kind of the gamut of the disorders I'm talking about today. If people do seem to have some issues there, then you really want to explore it in a number of different domains. One is to understand better the quality of the anxiety. So you can think of emotion or anxiety as having three different components, with both the physical manifestations, cognitions, which are the thoughts, which in this instance might be typically worries or fears, and the behaviors, which in this instance most commonly would be avoidance behaviors. So you want to get an idea kind of to what extent specific physical symptoms, thoughts, and behaviors are part of the profile for any given patient. You want to try to quantify the anxiety, so how severe is it? How intense is it? How much time is it taking up? Is the person walking around, feeling anxious all the time at a high level? Is it only occasional but intense, or occasional but mild? This is very critical. But most important is really how it's affecting the person's life. So one person can be having panic attacks every day, and they tough it out. They let it passes in 5 minutes. They go about their business. Somebody else can have a panic attack once every few weeks, but they're terrified it's going to happen again. They've constricted their lives. They're not leaving the house. A totally different story. So you really want to know how it's impacting the person's life. In terms of differential diagnosis, there's a little chart here to consider the different kinds of syndromes and how they cut across or are specific to different disorders. So I mentioned that panic attacks, each of these are kind of types of symptoms, not disorders, and these are disorders. So panic attacks can occur in any anxiety disorder. They can occur in depression. They can occur in a healthy person. In panic disorder, they're initially unexpected and they're persistent. If they occur in social anxiety, they're typically limited to a social situation. So you say, well, what triggers your panic attacks? It's going to be limited to situations where they're fearing embarrassment or in a social situation or anticipating a difficult social situation. And in generalized anxiety disorder, you can get panic attacks, but it might be related to worry. Typically, people will say, I was worrying for hours about this thing and just grew gradually until I felt panicky. In panic disorder, someone will say, boom, I was feeling fine, and then suddenly I got this terrible symptom. So anticipatory anxiety can occur across all these disorders. In panic disorder, it's typically anticipatory anxiety about situations that might trigger the panic, so they've got to go into the subway and they're feeling anxious about that. For social anxiety disorder situations, it's typically limited to the social situations. People might worry, though, for weeks ahead of time about some speech they've got to give at work. And in generalized anxiety, it's typically across a variety of different domains. Similarly, with the avoidance behavior, it can occur in any condition, but it has some specificity to the nature of that disorder. So in panic disorder, it's typically agoraphobic type avoidance, fear of closed spaces, being alone, crowds. But people can also experience fear of social situations. They might feel they would get, if they had a panic attack in a social situation, it would be very embarrassing. People in social anxiety, again, typically will avoid social interactions, sometimes things that are easily avoidable at optional situations, and in more severe cases, they may even be avoiding important things, school classes that they can't tolerate even just sitting in the room. The typical cognitions that happen, again, are related to the nature of the condition. So people with panic disorder will often have fears during their panic attacks of extreme events like dying, losing control, having a stroke, having a heart attack. It's much less common to have that kind of intense fears outside of panic disorder. So in social anxiety, the fears are more interpersonal, about fear of embarrassment, fear of humiliating themselves, fear that others will think badly of them, or fears that you're going to make someone else feel very, very awkward by your awkwardness. In generalized anxiety disorders, I mentioned, it can be across a broad number of domains. The physical symptoms overlap quite a bit across different anxiety conditions, but there's some differentiation. And as I mentioned, in panic, you're more likely to get dyspnea sensations of shortness of breath, hyperventilating. People often get palpitations. They may feel lightheaded, related probably to the hyperventilation. Social anxiety, physical symptoms that are observable to others tend to be the most troublesome, like blushing, sweating, and trembling. And generalized anxiety disorder is defined by having certain symptoms like tension and insomnia, so they tend to be more frequent. The typical behaviors across these, again, avoidance, but it really depends on the nature of the fears and what kind of situations a person might avoid. So a way of conceptualizing this pattern of these symptoms, the anticipatory anxiety, the avoidance, the fear in the situation, is through this kind of vicious cycle that maintains the fear and avoidance. And so people have some feared situation, whether it's something that seems to have occurred out of the blue or through some traumatic event. They have some fear in the situation. They now start avoiding their feared situation. So avoidance has the benefit of reducing anxiety. If you don't feel like you have to go into the situation, at the moment, it tends to give you temporary relief, which then has a negative effect of reinforcing that avoidance. So, okay, I avoided it, I feel better, I'm going to keep avoiding it. The trouble with avoiding things that you really need to do is that when you actually have to do it, the fear becomes greater. So it amplifies the fear component here, and you get stuck in this kind of vicious cycle. A lot of patients very much relate to that kind of concept across disorders. And This kind of conceptualization also provides the basis for the best established kind of psychotherapy approach to these disorders, which is cognitive behavioral therapy. And cognitive behavioral therapy tries to interfere with this process in a couple of places, mainly interfering here, saying, even if you have the fear, we need to figure out some ways for you to stop avoiding the situation. If you put yourself back in the situation with some coping tools, maybe some thoughts to help you cope, some maybe physical behaviors like breathing exercises to help you cope, and you have a better experience in the situation, then you'll, instead of learning that avoidance helps, you'll learn that I can tolerate it, I can manage it, and this cycle can kind of reverse itself, and you can be in situations and have a positive experience and feel less fear the next time. So, so as I mentioned, cognitive behavioral therapy has been quite well studied at this point. Some studies comparing it to medication for anxiety disorders find it roughly equivalent in effectiveness. For any one person, one approach may be better than the other. The main components to it typically are, one is a cognitive component, so identifying fearful thoughts that are irrational, helping people look at those situations more realistically, helping people have more helpful thoughts purposefully when they're about to go into a situation. Practicing exposure, so again, the opposite of avoidance is exposing yourself to what you fear and learning that you can tolerate it. And sometimes incorporating relaxation techniques like breathing exercises or muscle relaxation exercises to help the person manage their physical symptoms when they happen. Typically, CBT is done over weekly sessions, typically 10 to 20 sessions, though it can vary a lot depending on the nature of the condition and the person. And depending on the disorder, some specific kind of techniques can be useful for that. In terms of medication, again, I'm just going to give you a kind of quick overview of this at this point, but the first line medications for each of these anxiety disorders are the SSRIs, the serotonin reuptake inhibitors. Some evidence also for serotonin norepinephrine reuptake inhibitors, particularly venlafaxine. And there are quite a few controlled trials at this point in panic disorder, social anxiety disorder, generalized anxiety disorder, all showing similar kind of levels of efficacy. The exceptions are in specific phobias like fear of flying, fear of particular animals. We just don't have any data on the effectiveness of these kinds of medications for those conditions. And they're usually not that practical because these are medicines taken on a daily basis. If somebody's got a fear of flying and they only do it once a month, once every 6 months, it may be more sensible to take a PRN type of medication if you're going to use a medication for that issue. So the SSRIs are the first line because of really a balance of good efficacy, similar to other medications, but the combination of good efficacy and fairly high tolerability. In anxiety disorders, it may take longer to see a benefit, so whereas in depression, people typically use 4 weeks as the time where people are likely to show benefit. It may take up to 8 weeks to really see a clear effect in anxiety disorders, although some people may notice improvement in the first couple of weeks. And there's no evidence for any particular SSRI within this class to be superior. Just to give you a feel for one typical kind of response profile, this was a study of generalized anxiety disorder, comparing, happened to be venlafaxine here, an SNRI medication with placebo. It was a long study. Most of these studies typically are 12 weeks. This was a 28-week study. And we're looking at severity of symptoms on an anxiety rating scale called the Hamilton Anxiety Scale, where people start out with quite significant symptoms. It's a little it's cut off here, but if you get down below 10, you're pretty much symptom-free. And so what you can see is that the groups begin to even statistically separate out in the first couple of weeks, even though improvement is gradually occurring over the course of 6 to 12 weeks. And there's a big placebo effect, which we commonly see in anxiety studies. But the placebo benefits in this study plateau, where people on the drug continue to show further improvement, and the improvement's maintained over the course here of 28 weeks. Another way of cutting this is looking at it categorically. what's the response rate? How many people have a significant improvement that makes a difference in their quality of life? And this has been defined different ways. Here's two different, well, here's a definition here. A 50% improvement, a bit arbitrary, but it seems to correlate with a significant clinically meaningful improvement. And here, these are, so again, we're looking at generalized anxiety disorder studies, a different medication, escitalopram and SSRI, several studies pooled, so it's a big sample. About half the people had a significant improvement, about a quarter on placebo. That's highly significant. And that's kind of typical. If you look at across anxiety disorders at rates of significant improvement with a single course of SSRI treatment, 50, 60, 70% are typical response rates. And that's typically double what we see on placebo. If you have a higher criterion of saying who's really remitted, who's virtually free of symptoms, only about half of the responders would meet that criteria. So here about 25% were fully remitted, again doubling the placebo rate. So these medicines are very effective, but typically people still have some symptoms after a course of treatment. Other medicines include benzodiazepines. These are kind of the prototypical anti-anxiety medicines. They've fallen out of favor over the years, and as we have medicines that are safer, like the SSRIs, but they're still very useful for their short-acting benefit. They're useful for as-needed use, whereas the SSRIs are not useful in that way. They're not a first-line treatment, though, because of the risks during chronic treatment, the risks of withdrawal effects when they're stopped abruptly. They have some abuse potential. They can cause side effects of sedation, and they can cause cognitive effects and interfere with balance. And it can be a big problem, especially in the elderly. But they do remain a second or third line treatment for conditions like panic disorder and social anxiety disorder, where they've been shown to have an ongoing benefit for people who take them over longer periods of time. There's a variety of other drugs that have been studied. Usually, most of these have only been studied in 1 or 2 or 3 controlled trials, so they're kind of fallbacks when other things don't work. They include buspirone, which is a 5-HT1A agonist that has been shown efficacy in generalized anxiety disorder. There's some other antidepressant medications that have different mechanisms that seem to be useful, including mirtazapine, and an older class called MAO inhibitors, which are very effective but have high risks, including a risk of a high blood pressure reaction if they're combined with certain foods. Also at risk with some opiate medications. Other medicines, gabapentin and pregabalin, have some anti-anxiety effects, and again, another older class, the tricyclic antidepressants, had been previously shown to be effective for panic, but not used very often today due to higher rates of side effects. And just to put in a plug for my research group in the Anxiety Disorders Clinic at PI, we have ongoing studies in many of these disorders. We do clinical trials. We do brain imaging studies and other studies trying to understand more about the causes and neural correlates of these conditions. Thank you.
I'll get rid of all signs of the professor of psychiatry from the recording and the PDF, just so nobody can say it's misrepresented.
That's right. Professor, over here.
Last year, it was funny that class would interrupt lectures to ask questions. I don't know if you remember, but people were raising their hand in the middle of lectures. Do that, but they're very engaging.
That's good.
Yeah, it's a little more cooperative. Yeah.
It's interesting each class has their own style.
Even though we've been recording the lectures, I mean, that's how I am.
Okay, well, thanks.
All right, thank you.
See you next year.
I
because of
insist
the
on going to try to
section.
protect my section already.
Yeah.
They're so.
Yeah. Yeah.
Anyway.
Yeah, you're the only one. I mean, I'll have 4 meetings because of the site med and the clerkship, but you're going to have more than